data log IR. Yes.
Thank you very much, John. All right, good morning. It's pretty exciting because we have a data log session. So I've been doing work on data log from the PL side for like 10 years now, but I don't think we ever had a data log session at one of the major SIGPlan conferences. So that's pretty cool. So data log. Data log is a rule-based language. You have rules like this. This is the typical example many of you may have seen, but I'm going to repeat it for those who are new to data log. So we have a path, and you have a path from A to B if there's an edge from A to B. And you have a path from A to B if there's an edge from A to C, but also a path from C to B. So that computes the transitive closure of the edge relation. Okay? And so then you take some data, which here would represent the edges, and you compute some relations, which here would represent the transitive paths. All right, so data log comes from the database community originally, and they dealt with small queries running against large amounts of data. Okay? But now we're doing data log at PL, right? And we have a lot to contribute, but there's a slightly different setup. So the queries that we consider here in PL, they're typically much larger, and the data is relatively small compared to what's used in the database community. And so one of the examples of things that we do in the PL community is write program analyses in data log. And so here's a small extract of points to analysis for Java, which is part of the dupe analysis platform. And actually, this is really a small excerpt. So here's a graph that shows nodes. Each node is a relation defined in the data log program, and the edges are their interdependencies. Right? So this is a data log program with hundreds of relations. They all have complex dependencies on one another. And it's really difficult. And these are the kind of programs we deal with in PL. OK, so what are the PL research questions about data log? Well, from what I can see, it's mostly these three. It's performance, expressiveness, and programmability. And because we care about these aspects of data log, a growing number of data log dialects have been proposed in the literature. So here's some of them. You may have heard of Soufflé. It's one of the most well-known ones in PL. Inca is one that we are developing. Then there's some older ones like BDD, BDDB, Daedalus, Agglog, Formlog. We will hear more about Formlog today, QL, and so on. And so traditionally, all of these data log dialects also come with an engine. Right? And so you have different data log engines, and there's like a one-to-one mapping between the dialect to the engines. OK, so that's not so great. And what's the problem here? Well, the first problem is interoperability is lacking. So we have no source interop. That means if I write a program in Soufflé, I can't use it with the solver of Inca. Right? We also don't have binary compatibility. If I have two programs, one written in Inca, one written in Soufflé, I cannot link them together. I can't use them together. Okay? And if Soufflé implements an optimization, the other data log engines either have to re-implement it or not have it. And so one of the solutions we know from compiler frameworks is we can design an intermediate representation, a data log IR. And then all of the dialects first translate to the IR, and then we translate the IR to all the backends. Okay? But here comes problem 2. The second problem is that the data log dialects all define custom extensions to data log as you know from textbooks. So for example, Soufflé has algebraic data types. Inca and Formlog have functions. Daedalus has state. These are all things that don't exist in textbook data log, and what you would also not in the data log dialects you see in the database community. OK, so we need a more sophisticated design. And so let's zoom out a bit. And instead of having one data log IR, we're going to design, or we have designed, a core data log. And that's really like textbook data log, which is extensible. So you can write lots of extensions to this IR. OK, and then something like Soufflé, the Soufflé compiler front end actually uses a whole bunch of these extensions like booleans, numbers, algebraic data type aggregation, disjunctions, and so on, right? And it can generate not just core data log, but also using these IR extensions. But we still have a problem. The problem is the Ascent solver, which is one data log solver written in Rust. the send solver now seems to have to implement all of these extensions, right? And that's not so great either. So what we do is we actually design a multi-level IR where you have lowering steps. Lowerings are like the sugar rings, but between IR extensions or towards the core IR. And that means that in the compiler backends, you only have to implement those things that cannot be lowered. Okay, and then we add one more thing. So in this paper, and this is also the focus of the remainder of the talk, we add static typing. And we want static typing in a way that you can define extensions. And these extensions can very precisely declare their static semantics to make sure that, well, two things. So first, optimizations can assume you have valid code to begin with. And secondly, there's a lot of code generation going on now. We have the lower rings, we have the compiler front ends targeting the IR. And we know code generation is really difficult, and type systems help with figuring out when something goes wrong. Okay, so what we end up with, and that's also the title of this talk, is a typed multi-level data log IR. Okay? And so in the remainder of the talk, mostly I'm going to talk about the type system and its design, which I think is pretty interesting. So let's look at what kind of type system we need for data log. So, and we're going to start with core data log. Well-typed core data log programs are not supposed to go wrong. So what can go wrong? Well, first we have what you expect. We have kind of type compatibility issues. So for example, if I'm trying to add a string and a number, that shouldn't be allowed because they don't have compatible types. Or if I'm declaring that the column X of relation city has type string, but then I'm assigning the number 3 to it, to a logic variable that will feed into that column, that shouldn't be allowed. So we can have incompatible types. There's nothing particularly interesting about this aspect of the type system. And so what's interesting instead is reasoning about variables. Because we have logic variables in data log, and we want extensions to be flexible in the way that they can introduce bindings and binders, and we will see more of this. So what are the kind of problems? So this rule is invalid. It's invalid because we're using X as an operand to multiplication, but operands cannot bind variables. So at this point, X is unbound. So in data log, you're trying to compute the X's that satisfy the constraints on the right-hand side, right? And so this rule cannot be solved by a data log solver because we don't know what X's to put into the column, right? And the problem here specifically is you cannot bind variables when they are in an operand position. Here's another example. This relation has two output parameters, A and B, but we're only binding B. And this is a property known as range restrictedness in the data log literature. And that's an example where the variable has to be bound, but it is not. Here's another example. This is a data log relation, again, two output parameters, and the body is an equation constraint. And equations are kind of good because they do bind variables. If you do, like in our city example at the top, right, we have x equals 3, and that binds x to 3. But if you do a equals b, and neither of them is bound yet, then this constraint cannot be solved. And then finally, one more example. If you have negative calls are like checking that something is not in a relation. And since the complement of a relation is not necessarily computable, you actually need to know what you're checking for. So you need to know what A and B are before you can check if they're not in path. And again, in this example, A and B are unbound. So how can we reason about the boundedness of variables in data log in a way that it's precise and extensible by extensions? Okay, so let's look at this rule again that we saw at the very beginning of the talk. It's the transitive closure path rule. So we're going to distinguish the status of variables, and we're going to mark them, decorate them in the program. So the open circle says it's a binding occurrence. So this is the place where x gets its value, whereas the bullet is a bound occurrence. This is where you're reading the variable. And now we can annotate the rule with this notation. And so what we get is, in the first atom, edge AC, we're actually binding AC to the tuples that are in the edge relation. And then the second atom, we're reading C, it's already bound, and we're using it to bind B. And so this binding information actually shows us kind of what the underlying index structure is going to be of these relations, which is also nice. And then in the end, we can check that A and B in the head of the rule actually must be bound. These must be bound occurrences, right? Otherwise, we're violating the range restrictedness. And so here's the second example, it's kind of the same rule, but a little bit refactored. A and C are again bound in the edge atom. Then we have an equation. That equation acts as an assignment. You're assigning C to D, and that's because C was already bound and D was not. And then you can use those again to query path, and A and B are bound in the end. So kind of this is an observation of how this information of boundedness flows through a rule. And by the way, we're forcing evaluation order here, which is left to right. So we can take this now and start designing the type system. So here's the typing context. A variable can be unknown, or it can have one of two statuses. It can be declared, which means that we know its type, but we know it's not yet bound. Or it can be bound, which means we know its type and we know that we can read from it. Okay, and so if we take this context, then we can start designing a type system. So here's the first approach, the first try. We designed a bidirectional type system, which is flow sensitive. It needs to be flow sensitive because the binding of variables kind of happens on the fly during the rule. And then we get these kind of judgments. They're pretty standard. Term checking is like expression checking in other languages. You have a context and a term, and checking means you are given the type, and you compute the resulting context. And term inference is the same, but you're also computing the type on the fly. And then there's atom checking. And so I'll just show you two example rules. So here's one rule that says, if you want to check a variable and you're given the type of that variable, then after that variable occurred, it's bound and has type T. And then here's another one. This is for equations. For equations, there are two rules. I'm only showing one. You need to infer the type on one side of the constraint or on one side of the equation, here for T. And then you can use that type to check on the other side of the equation, here, U. Okay? So that looks kind of promising. And indeed, for the examples I showed before, this works out fine. So you can use these rules to actually show that A and B will be bound at the end of this rule. But they don't work for the kind of the counter examples I showed. So let's go back to the square root 4 rule, where we had x as operands. The typing rules we've designed so far cannot distinguish whether we are in a position where binding is allowed or not. And that's why what it will do is when x occurs as an operand first, we will just bind it. So that becomes a binding occurrence. And then the second operand is reading. And that doesn't make any sense whatsoever. So there's clearly something wrong here. And so there's one thing we need to add. And that's kind of what I think is the most interesting novel design aspect of this type system. And we need to make it bipolar. So bipolar is basically just a Boolean flag. And so the judgments now have this polarity, which is either positive or negative. And what it means is this. If the judgment is done with the positive polarity, we are lenient. We allow bindings to occur. But if we have a negative polarity, then we are strict. We don't allow any new bindings to occur here. Okay, and so here's an example. So let's do the multiplication rule. That was the problematic case in the square root rule. And the multiplication rule now can be explicit about whether it allows bindings to occur in the operands or not, right? And what we do here is we say, okay, we can check T and U. We know the type that we expect. And the polarity is negative, which means no bindings allowed, right? And we can do something similar for equations, right? We had this problem where on both sides of the equation was an unbound variable. We can disallow this by requiring that we need to have one side needs to be checkable in a negative polarity, so without doing new bindings. And then the other one can bind, so we can have assignments. And so this is pretty nice, and it's actually also extensible. So I'll just show you two extensions. So this is for nested disjunctions. Nested disjunctions This kind of a standard technique from flow-sensitive type systems. So we do the meet of the two resulting contexts, which means only those things bound in both alternatives are guaranteed to be bound. But one of the most interesting thing is actually negation. So what is the polarity of negation? The polarity of negation is really just the flipped one. So if you want to check if not A is valid, it's enough to check A, but you negate the polarity. And then you get this nice property of double negation elimination that we would expect, but now the static semantics actually explains also that that's what we do get. So what happens here is if you have two negations, you flip the polarity once, you flip it twice, and that means you're back to where you started. And so effectively, we have eliminate the double negation in the static semantics. Okay, and this is really flexible. I don't have time to show you how flexible it is, but we've implemented the system and we've developed a lot of different extensions. I'll just mention a few highlights. So we have a lot of first-class data structures, records, lists, sets, and maps, and we can precisely describe their binding structure. We have demanded parameters, which is like giving the programmer a handle into the magic set transformation. You can say this parameter needs to be bound and the binding needs to come from the outside. And this is kind of really playing around with the binding structure. Parametric polymorphism, stateful variables, and all of these extensions, a lot of them actually need to use the polarities very smartly to have the static semantics be precise. And so what you get by using all of this is this type multi-level IR. And this is really cool because it allows us to do something that wasn't possible before. What we can do is we can take a single source program, translate to the IR, and then target one of different data log backends. And what we did in the paper, just to illustrate that it's possible, is take one dupe points to analysis and translate it to different engines. And we can actually now compare the performance that these systems have on the exactly same program. Because what you've done, what you see in the literature so far is that people have hand translated the data log programs to meet the different dialects constraints. So one question you may have is, how much effort is it actually to develop these compiler front ends? That's something we discussed in the paper. I just want to, show you the kind of the key result here. And because we have all these IR extensions which are reusable across front ends, writing the compiler front end itself becomes really easy. So for example, we have about 300 lines of code to compile Soufflé to our IR. We have about 250 lines of code to compile a fully functional programming language to Datalog, and an object-oriented language that David will talk about in the session later. That's a little bit more effort, but still very much manageable. And so for the functional programming language, we had a compiler before, and this gave us a 10-fold reduction in code size. So let's summarize. We developed a type system, which is bidirectional, flow-sensitive, and bipolar. And we show that you can use that to precisely describe the static semantics of Datalog. And it's also extensible in a way that extensions can very precisely manage their own bindings and how they change bindings. And then we've implemented this in an open compiler framework that we've implemented in Scala, and we have developed or implemented 4 front ends for that framework so far in 3 backends, and a module system that we presented at Gypsy here at Splash as well. And now the next goal for us is actually look at IR optimizations that can apply and be useful across all these different backends. Thank you very much.
Hi, thanks for the talk. It seems like very interesting work. I was curious, when you were talking about the polarity, it reminds me a bit of the modes from some Prolog systems. Is there any connection, or am I just imagining that? Thanks.
Right, thanks for the question. So the modes in Prolog, they're on the parameters of the rules. And I would say that the polarities is a generalization of that. Okay. It's a generalization in the sense that you can have that at any place during the typing derivation. And not just at the parameter. So the not rule illustrates this a little bit, where in the middle of the Datalog rule, you can have not of something, and you're actually just negating this.
Okay. Yeah. Thank you.
Good question, thanks.
I'm more concerned. Hi, great talk. I'm more interested in some of the practical part of this. So like, what we're giving up by doing this IR, I guess. So if we have like souffle front end going through your IR into the souffle back end, how does it compare to souffle out of the box? Both in like, you know, would you end up with the same problems being posed to the souffle back end, or is it, you know, does the lowering do the lowering differently than like souffle out of the box would today, if that makes any sense?
So if you have a souffle source program and you basically pipe it through our framework, the resulting souffle program would be almost identical to the original one. And that's because the compiler backends can choose which lowerings they need. So oftentimes when a compiler backend already supports some extensions, then we would leave it to that compiler backend to do the lowering internally.
I see.
Okay.
Okay.
Which is a choice, right? We don't do it for everything, but for some of these things.
That makes sense.
But so that's a choice. And in general, now you can describe very complicated pipelines where you choose what to lower when. And in particular, the compiler backends don't need to support all the extensions either, right? Just the ones that cannot be lowered.
Makes sense. Thank you.
Yeah, thanks.
Okay, let's thank our speaker again. Zhang, and he will be telling us about finding bugs.
Okay. Hello, everyone. I'm Zhang from Nanjing University. I'm happy to be here to present our work on a no black box approach in finding cross-rule optimization bugs in data log engines. This is the joint work with Lin Zhang Wang from Nanjing University and Manuel Riga from National University of Singapore. Datalog is a popular logic programming language supported by deductive database system. Datalog has been applied in many important domains, such as program analysis, distributed systems, program understanding big data, and some other important domains. So it is crucial that the Datalog engines work correctly. I use an example to introduce what is Datalog. Suppose you want to find the reachable nodes in a graph based on its edges. Then you can use this Datalog program. In this program, the relation edge presents a real edge between the two nodes in the graph. For example, if there is a fact edge 1, 2, means there is an edge in the graph between node 1 to node 2. This program takes 4 edges as input. There are 2 rules that define the relation reachable. The first rule computes the directly reachable node based on its edges. And the second rule computes the indirectly reachable nodes based on the existing reachable nodes and edges. For example, node 2 is directly reachable from node 1 due to the edge 1, 2. And since there is an edge from node 2 to node 3 becomes indirectly reachable from node 1 through node 2. Executing this program with the Datalog engine, we can derive all the reachable nodes in the graph. There are many major Datalog engines, and these 4 are among the more well-known. Souffle is widely used in many projects, including DOOP, a Java static analysis framework. CodeDB is designed to support machine learning and has obtained over 3,000 stars on GitHub. DDLog is developed by VMware with over 1,000 stars. Muse was used as part of this tree, a well-known constraint solving tool. Many cross-rule evaluation strategies are applied in Datalog engine to efficiently evaluate rules. For example, the bottom-up method evaluates all rules to derive the complete set of results. In contrast, the top-down method only evaluates the rules that are related to the output relation. There are also many optimizations, such as magic set transformation, which improves performance by rewriting the rules. These optimizations typically require careful consideration of the relationships between rules to ensure the correct execution. Our goal is to find cross-rule optimization bugs in datalog engines. Logic bugs can cause datalog to silently produce incorrect results for a given program, and cross-rule optimization bugs are logic bugs that are caused by cross-rule optimizations. The main developer of Souffle also emphasized in the recent keynote that designing novel automated testing tools for datalog engines is one of the main open challenges in this domain. Test case generation and test oracle are two main key challenges in fuzzing, both of which we aim to address. So let me first introduce what is logic bug. This test case triggered a logic bug in CodeDB. After the first three rules, there are three facts: node 1, age 11, and age 01. The expected output for this test case should include both 0 and 1. However, CodeDB only generates 1 as the result. The developer of CodeDB gave us feedback that the worst thing a database can do is to give wrong output. This bug was caused by an error in the sim-naive algorithm, which is a bottom-up evaluation strategy. An intuitive idea to detect optimization bugs would be to apply differential testing. Differential testing means providing some inputs to two or more comparable systems with the expectation that they produce identical results. But different datalog engines share only core features, so it is impossible to test other important features. Most datalog engines do not offer optimization options, making it challenging to apply differential testing within a single datalog engine. To detect cross-rule optimization bugs in datalog engines, we propose a new black box test approach named incremental rule evaluation. We incrementally build the test case and individually evaluate the new added rule. This approach allows us to disable all optimizations that would typically be applied when multiple rules are present, while also enabling the generation of complex test cases that produce non-empty results. The core idea behind our test oracle is to execute each rule in the test case individually, thereby disabling all cross-rule optimizations. This is the overview of our approach. Our approach begins by generating the initial inputs and the definition of corresponding relations. Then we enter the iterations and generate a rule in each round. To determine the execution order of the reference program, we construct a precedence graph in which each node represents a rule and each edge indicates a dependency relationship between the nodes. The reference program is then evaluated based on the order determined by the precedence graph to obtain the reference result. Finally, we evaluate the optimized program and compare its output to the reference result. Any discrepancy indicates a logic bug. Now I provide more detailed information on our approach. To begin, we initialize the input and generate the corresponding relations. Here we generate two facts as input, in 0 and in 1. In the first iteration, we generate the first rule based on the initial relations. Here we define a new relation as the output of this rule. Here is A. This will introduce a new relation into the test case. We derive the output, the result of this rule from the datalog engine and check it. If the result is empty, we remove the rule with a high probability and generate a new one to avoid having rules with empty results. This is necessary because an empty relation can lead the datalog engine to compute an empty result for other rules that's dependent on this relation. However, some bugs require an empty relation to be triggered. So we introduce this probability. We also verify that the newly added rule is valid and does not cause any semantic error, which can be challenging in random test case generation. The random method lacks knowledge of the facts derived by rules, and a certain specific value can trigger errors, such as division by 0. Then we add this rule to the optimized program and obtain the optimized results. We verify that the results obtained from the reference program and the optimized program are identical. In the second iteration, we generate the second rule and do the same things as that in the iteration 1. We can see here the reference program only contains a single rule, while the optimized program contains 2 rules. The reference program also requires additional facts as input. Here is A0 and A1, which are the outputs of the first rules, as relation A appears in the rule body. Last, if there is an iteration N in which a discrepancy is found between the results of the reference program and the optimized program, we consider that the test case to have triggered a logic bug. Or if the number of iterations reach a predefined limit, indicating that the optimized program is sufficiently complex, we end the generation of the current test case and move on to the next one. With this approach, we generated this motivating example step by step and detect this bug in the 4th iteration. However, there are cases where our approach cannot be directly applied. Specifically, if a previous rule depends on a newly added rule, we must re-evaluate these rules to ensure that all rules reach to a correct fixed point. The execution order of these rules determine whether the correct fixed point can be reached. This is an example that involves regression, with the negation palace outside that regression. This is a precedence graph that illustrates the dependency relationships between the rules. To determine the correct evaluation order for each rule, we use a well-studied solution from datalog engines, stratified datalog, which is designed to handle negation in datalog engines. Stratified datalog first divides the precedence graph into different strata, where rules in a lower stratum depend on rules in a higher stratum. Rules that form regression are placed within the same stratum. Then we execute the rules sequentially from the top stratum to the bottom. For rules within a same stratum, there is no specific execution order if there are no dependency relationships between them. For rules involved in regression, we need to evaluate them iteratively until no new facts are derived, indicating that all the rules have reached a fixed point. The input for each rule should consist of the necessary facts derived from the higher strata as well as the same stratum. Finally, for this program, we will obtain the following execution order. So for the newly added rule O3, we need to re-evaluate R0 first, then iteratively evaluate R1 and R2 until there is not any new fact is derived. Means this regression reaches the fixed point. However, if there is negation within a regression, we cannot compute the fixed point by evaluating the rules individually. For example, we add a negation at the rule R2. This case falls outside the scope of stratified datalog, and most datalog engines do not support this language feature. This is supported by another language, Prolog. So to address this challenge, we put all the rules in this regression into a single reference program to derive all the facts generated by these rules. While this approach may not directly detect bugs within the regression itself, it can still identify bugs arise between the regression and other rules. We implemented our approach in a tool named DOPT and selected 4 major datalog engines for evaluation. And then evaluated it with the following 3 questions. First, how effective is DOPT in finding new bugs? And how does DOPT compare to the state-of-the-art approach? And last, how do DOPT's components contribute to its overall effectiveness and efficiency? For the first question, DOPS found 30 unique bugs in 3 major engines, and 13 of them are logic bugs. We also found a logic bug in DDLog. However, this was the only one bug that a state-of-the-art approach found in DDLog, and it has not been fixed yet. Here is the state of the bugs found by DOPS. 6 bugs have been fixed, and 13 have been confirmed. We conduct a comparison for the second question. QFast is the state-of-the-art approach to detect logic bugs in DDLog engines. We found that out of the 13 bugs detected by QFast, only one could not be identified by our test oracle. This bug occurred within a single rule, making it unclear how to apply our test oracle in this test case. And for 13 bugs found by DOPS, 5 could not be found by QFast. There are 2 reasons why QFast missed these bugs. First, its mutation approach is limited to conjunctive queries, which means some language features are not supported. Second, QFast is unable to prevent the application of certain optimizations, so making it ineffective to detect bugs related to those optimizations. Our tool offers multiple configurations to control the testing process. Here we present only the most important one. We compare the efficiency of our incremental test case generation approach with the naive random one. For the random approach, we generate the entire test case at once and then execute each rule individually to create the test oracle. We run this experiment for 24 hours with different test case size. We have 3 metrics. The first is the total number of test cases generated by these 2 approaches. And the second is the total number of valid test cases. The last is the total number of test cases with non-empty results. We found that while the random method always generates more test cases, our incremental approach always produces more valid test cases on Souffle and more test cases with non-empty results on DDLog. Lastly, let me conclude my talk. This work aims to identify cross-rule optimization bugs in DDLog engines. We proposed an incremental rule evaluation method that generates the test case and the test oracle in the same time. Our approach found 30 unique bugs across 3 major engines and demonstrated the ability to generate more valid and non-empty test case compared to the random method. That's all. Thank you all for listening.
All right, we have time for a few questions. And again, please come up to the mic if you want to ask a question.
Hi. I mean, also in relation to the talk I gave before, how much effort did you have to spend in order to target these different data log backends? Like how did you address that in the test generation?
Okay, I think our approach is easy to implement as we just reuse the data log engine under test and we just split the rules and run them one by one. So we don't need too much effort to implement the tool.
But, so I'm not sure I understood. So you generate the rules, right?
Yes.
And you have separate generators for each data log backend, or do you generate them in one dialect and then translate between those, or how does that work?
You mean for different data log engines?
Yes.
Yes. I think the core algorithm can reuse by different data log engines, but the generation of the generation of the test case of each data log engine still needs some effort.
Okay. Thank you.
Okay, well, let's thank our speaker again. Okay, our third talk will be by Aaron Babenik, and he will be talking about making Formulog fast.
Cool, great. So yep, I'll be talking about making Formulog fast using unconventional data log evaluation. This is joint work with Michael Greenberg and Steve Chong. So before I get into our contributions, I'll give just 2 slides of background. If this works. That's okay. Okay, so what is data log? Well, we've seen it a couple times already today, but the way I'm going to present it is as a way to mechanize inference rules. So here we have inference rules, 2 of them, that compute reachability from the node, from the root of a tree. Data log allows us to stick these inside a data log engine, provide a database of input facts, and the data log engine will produce for us output facts, like which nodes are reachable in the tree. How does it do this? It's going to use a bottom-up fixed point computation. A lot of data log engines are highly optimized, so this can scale to making tens or hundreds of millions of logical inferences. One of the big applications for data log over the last decade or so has been program analysis, because it's been found that analyses like points-to analysis can be encoded both very naturally and effectively in data log. A couple years ago, my collaborators and I took this a step further by developing Formulog, which combines data log and SMT solving. It also has some functional programming, but I'm not going to talk about that today. The motivation of Formulog was to extend the benefits of data log to SMT-based analyses like refinement type checking or symbolic execution that you can't encode naturally in traditional data log. So Formulog allows you to mechanize inference rules like this one, where you have SMT formulas occurring as terms within the rules, and then you also have SMT queries, such as checking for satisfiability. And what happens is when you evaluate this Formulog program and you get to the satisfiability query, it's going to be sent off to a pool of external SMT solvers. And the key thing is that for a Formulog analysis, the SMT solving component can be one of the largest parts of the computational workload, unlike a traditional data log analysis. And that leads to really the question at the heart of this talk, which is if we have one of these Formulog-based analyses that uses a lot of SMT solving, we want to make it faster. How do we do that? Are the traditional techniques for high-performance data log sufficient? Or do we need something novel that better accounts for that SMT workload? And we'll explore both approaches in this paper. So we make the following contributions. We developed a compiler from Formulog to Soufflé, which, as it's been mentioned, is this existing, well-known data log system. We've developed a novel data log evaluation algorithm called eager evaluation. We've implemented eager evaluation in both Formulog and Soufflé. And then combining our compiler with this new data log evaluation algorithm, we've achieved speedups over published analyses written in more traditional languages. So I'll talk about all these contributions, but I'm going to start with the final one. So with the techniques we developed in this paper, Formulog is a competitive analysis platform. What do I mean by that? So we've been able to encode a range of sophisticated SMT-based analyses in Formulog. We've been able to run them on substantial workloads in terms of the number of logical inferences or the number of SMT calls or both. And we've achieved good results. So on 20 out of 23 benchmarks, the Formulog version has actually beaten the version written, like the handwritten version in F#, Java, or C++. So I hope this makes you excited to learn more about how we're able to achieve these results, because that's what we'll be talking about. So the first thing we did is we developed this compiler from Formulog to Soufflé. So Soufflé is a high-performance data log system, and by compiling to Soufflé, we're able to take advantage of the traditional techniques for making data log fast. Like Soufflé really embodies those techniques. How well does that work for Formulog? Well, it gives us some speedups over our baseline Formulog interpreter, but they're not evenly distributed across the case studies. So the case study where we don't use much SMT solving gets the biggest speed up, and the case studies where we use a lot of SMT solving don't get much speed up, which makes sense since those traditional techniques are really only optimizing that data log component of the workload. And that leads to the natural question, like how do we do better for these SMT-heavy analyses? Well, our hypothesis is that semi-naive evaluation, which is really the bedrock of high-performance data log systems, is actually not a good fit for these SMT-heavy workloads for two reasons. One, it batches work, and two, it performs essentially a breadth-first search of the logical inference space. And we can see that in our little reachability tree example. The way semi-naive evaluation works is in this sequence of rounds. So in the first round, it computes everything that's reachable in 0 steps from the root of the tree. In the next round, it computes everything that's reachable in 1 step. In the round after that, everything that's reachable in 2 steps. So here we have this very explicit round structure that builds in batching. And then also, we can see that we're doing not only a breadth-first search of the tree, but this also corresponds to a breadth-first search of the logical inference space in terms of proof height. So why is this a bad thing for these SMT-heavy analyses? Well, let's extend our example and imagine that now we're doing reachability in a program execution tree, so something like symbolic execution, where our tree, now the edges are going to be labeled with SMT formulas. And there are 4 work items here, each one corresponding to a different edge to traverse. And I've annotated each one with sort of the SMT formula that needs to be satisfiable for that edge to be traversable. So the idea is it's reachability, but it's modulo the satisfiability of the path condition leading up to a node, like you'd expect in symbolic execution. So the first issue is that breadth-first search is going to limit the amount of incremental SMT solving that can happen, because typically adjacent queries are not going to share conjuncts. So we can see that here's the work items in breadth-first search order. We can compare this to what would happen if we did explore this tree using depth-first search. And we can see that there is sharing between adjacent queries. So some of those conjuncts are shared between the queries, which would give the SMT solvers more opportunities for incremental SMT solving and lead to faster SMT solving times overall. The second issue has to do with batching. And so if you have slow SMT calls, batching can exacerbate the way that those calls become bottlenecks. So here we have 2 threads, and we can see that thread 2 is waiting for a long time for thread 1 to complete if that green work item is like a long-running SMT call. If we don't batch them, everything is a lot more condensed, and the overall computation time is going to be shorter. So recognizing these limitations led us to develop this eager evaluation new data log algorithm. And whereas semi-naive is doing this batch breadth-first search, eager evaluation is going to do an unbatched depth-first search of the logical inference space. There's still some similarities. So both algorithms are parallelizable. They're both incrementalized in that they focus on novel inferences. So this is like the delta relations in semi-naive. And we'll see that there's enough overlap that eager evaluation is largely compatible with existing research and engineering on data log, which is a key to making this practical. So how does eager evaluation work? Well, in a nutshell, we can sort of split it into 2 parts. So you can imagine that you're partway through data log evaluation. You've made a bunch of inferences. One thing you need to do is choose which of these inferences to explore next. And the way that eager evaluation does this is through work stealing parallelism, which most of the time processes work using a last in, first out order. This in turn gives us something like an unbatched depth-first search of that logical inference space. In the second part, you've chosen that inference. Now you need to evaluate the inference rules on it to derive new inferences. Well, luckily for us, we can reuse the machinery from semi-naive evaluation. And this is really key because these techniques, so rule evaluation, is typically one of the most highly optimized parts of data log engines. And it's a key for the practicality of eager evaluation that we can use those. Eager evaluation is a work stealing based algorithm where work item is a rule specialized on a novel inference. So here you've derived that node A is reachable. You can specialize the rule for reachability on that inference, getting out this specialized rule that says everything that's an outgoing neighbor of A is also reachable. In eager evaluation, each worker thread is essentially going to perform a local depth first search. So this is the logic for each worker thread. You can think of this as like the logic for thread I. And I'll break it down into a few parts. So first, the thread is going to find the next work item. And the first thing it does is it looks in its own work list and sees if there is one there. If so, it will take it. Otherwise, it will try to steal a work item from another thread. So that's where the work stealing comes in. And the second part is when the actual work happens. So this is where the rule, which is the work item, is evaluated. New facts are inferred, and those new facts are then used to create new work items, which in turn are pushed onto the work list for the current thread. So two things to note here. So the first is that most of the time, work items are processed in this last in, first out order, and this gives us the depth first search. And the second thing is that this rule evaluation here is going to reuse that semi-naive machinery, as I mentioned. So that's eager evaluation in practice, in principle. How does it work in practice? So we've implemented it in both Formulog's interpreter and the Soufflé code generator. And our results are positive, that it's both practical and effective for these SMT-heavy workloads. First, we were able to add it relatively easily to both Formulog and to Soufflé's code generator. So amazingly, it only took 800 lines of code, which was pretty surprising. And the second thing is that it achieves speedups over Soufflé's standard code generator for semi-naive. So this is true even in the case of our Formulog interpreter. So the Formulog interpreter is something like 5 times faster than the code generated by Soufflé if it's using semi-naive. And if we compile eager evaluation, we get some additional speedup. So taking a step back, what does this mean for sort of our original baselines? So when I was talking about the compiler, I was comparing against the semi-naive interpreter for Formulog. And I was bemoaning the fact that for the SMT-heavy analyses, compiling them with Soufflé doesn't actually give that much speed up. What does this look like if we add eager evaluation to the mix? Well, it turns out for SMT-light analyses, this does not help you, actually hurts you a little bit. But for these SMT-heavy ones, we get some substantial speedups, which really indicates that this evaluation algorithm we've developed, eager evaluation, is a good match for these SMT-heavy workloads. So in conclusion, we've seen this compiler from Formulog to Soufflé. We've seen this new data log evaluation algorithm, eager evaluation. We've seen it implemented in both Formulog and Soufflé. And we've seen it achieve speedups over published analyses written in languages like Java and C++. What are the takeaways from this? Well, the first is that takeaway is that data log in general, and perhaps Formulog in particular, can be a realistic platform for these SMT-based analyses, at least as far as performance is concerned. And the second is that new data log workloads might require new evaluation techniques. So as has been mentioned earlier today, like data log has come a long way from its early days as a database query language of all sorts of new applications. We might expect that as these applications continue to evolve, we'll also have to come up with new ways of evaluating data log that better match those workloads. But that's one of the great things of working in a declarative paradigm like data log is that we actually have this flexibility, so we can do this. With that, I would just encourage you to check out Formulog on GitHub. We have a new tutorial about how to use Formulog to implement a refinement type checker. And thank you.
Have any questions?
Hi, thanks for the talk. Given I have a souffle program, I want to use the eager evaluation. What are the steps I need to take?
Like there, you just add a flag.
And then I guess you have evaluated the eager evaluation on a larger range of existing data log programs that don't have this S&T heavy load. So I'm curious to hear if the slowdown you observed in the one case, if that's generalizing to all the other ones or not?
So like in general, eager evaluation is not going to be a good fit for a lot of like traditional data log workloads. We've seen a couple cases where you have like doing reachability over trees where the trees have a particular structure with where like the finer grained parallelism of eager evaluation helps. But typically like the advantage with semi-naive is you have this batching, which is going to cut down a lot of overhead that eager would otherwise introduce.
Okay.
Yeah.
Thanks.
Cool talk, thanks. So if I understood this algorithm, so a couple of questions, right?
Yeah.
If I understood this algorithm correctly, it's a work stealing algorithm, so the speed up is all because of multi-core evaluation. Follow up to that, something that keeps coming up every time I read about data log evaluation, people start talking about top-down, but the lesson of 30 years seems to be that top-down evaluation doesn't work in practice, that semi-naive is all that we have. What happens, I mean, you seem to be in the same paradigm of semi-naive, you are exhaustively computing the fixed point. What if you decide you're not going to invoke the SMT solver at all because you don't care about some rules? Could top-down evaluation actually be helpful for Formula?
So the first question I think was about parallelism and like where the speed up is coming from. Well, so all the Formulog interpreter, the semi-naive version, and eager evaluation are both using the same form of parallelism internally. And then for Souffle, the semi-naive evaluation there is using OpenMP for parallelism. And then we're using like TBB's library for eager evaluation. So they're all, like all these implementations are parallel, yeah.
Yeah, but what about top-down evaluation? What if you don't want the full fixed point anyway?
Yeah, so I guess the answer would be you could apply like magic set transformation, and then that would cut out derivations that you don't want to do. I haven't thought too much about implementing top-down for Formulog.
Okay. Thanks.
Our final talk in this session will be by Zhenyu Yan, and it is about scaling abstraction and refinement for program analyses using graph neural networks.
Okay, thanks for your introduction. Hello, everyone. I'm Zhenyu from Peking University, and I'm honored to be here today to present our work. This is a joint work with Xin Zhang and Peng Di. And selecting good abstractions is a crucial problem in program analysis. Abstractions that are too precise tend to be slow, while coarse abstractions are often too imprecise, which means that they will introduce too many false alarms into the analysis. So it's important to choose abstractions that balance precision and efficiency, which means that it could eliminate most false alarms and run fast. Abstraction refinement is a method to find abstractions that are just precise enough. We start with the most coarse abstraction and run the analysis with it. Based on the result, we then select a more precise abstraction of the analysis. This procedure repeats until the abstraction is precise enough. Since we terminate once the abstraction is precise enough, the abstraction will not be overly precise. So, many abstraction refinement methods model the refinement selection as SAT or SMT problems. For example, one of the state-of-the-art abstraction refinement approach models the refinement selection as weighted max set problems, which tries to maximize the weighted sum of satisfied clauses. By solving the problem, it finds a minimal refinement to try. Since solving max set problems is NP hard, this approach is unscalable for large programs. Furthermore, the max set solver works in a greedy manner and cannot predict the effect after refining certain parameters, so it provides suboptimal refinements. Since neural network has shown its amazing power in many fields, our initial motivation is to use neural network to determine refinements. However, we face two main challenges. The first is that there are too many different analyses, and different analyses require different domain knowledge. So, how to develop a technique that could be applied to different analyses without feature engineering is a challenge. Second, neural networks are good at learning, so they can distinguish helpful parameters from unhelpful ones. However, in most cases, refining parts of those helpful parameters is enough, while refining them all can result in an overly precise abstraction which runs slow. So using neural networks alone does not work quite well. To tackle the generality challenge, we found that Datalog is a logical programming language which makes it suitable for implementing program analysis, so that different analyses in Datalog can all be represented as hypergraphs, which can then be transformed into graphs without feature engineering. So we can deal with those graphs using graph neural networks. Then, instead of using graph neural networks to determine exact refinements, we use their output to prune those max set problems, so that we can get problems that are much simpler. And by learning from helpful refinements, the result of graph neural networks can exclude some suboptimal solutions. Finally, we will use a max set solver to target the exact refinement. So our main contribution is proposing a general framework that could be applied to different analyses without feature engineering. To tackle the generality issue, we make use of the calculation of data log, which does not require feature engineering. And to make abstraction refinement scalable, to make abstraction refinement scalable, we use graph neural networks to simplify those mixed-set problems. And to find exact refinements, we use a mixed-set solver to determine refinements based on the output of the neural network. And to train our neural network, we design an algorithm to determine helpful refinements as our training data. Here is a pointer analysis example. There is an interface named dog, and two classes implement it. For every variable, pointer analysis calculates what objects it may point to. For example, since there is a new statement, variable teddy1 may point to a teddy object. For the assignment, every fact about teddy1 will be copied to temp. And how could we deal with function calls? Here, we invoke a function named id1, which simply returns its parameter. A straightforward idea is to treat parameter passing and return as assignments so that we could deal with them in the same way we deal with assignments. However, this is imprecise. Suppose another function also calls id1. Since there are two data flows into arg1 with different objects, arg1 may point to both a teddy object or a corgi object. So does teddy2. This brings in some imprecision, which is undesirable. The imprecision occurs because we use context insensitivity, which is a coarse abstraction. To improve the precision, we could use context sensitivity. First, we mark function invocations here from IA to IC. Then, we can distinguish different invocations to ID1 by considering it as two functions, so that the result of teddy2 will not be affected, and we can now get precise outputs. And though context sensitivity improves the precision of program analysis, it also increases the time cost of the analysis. It's practically impossible to use the most precise abstraction. Therefore, we need to select components to be analyzed precisely. For example, only refining IA here is precise enough. However, if we choose IC, since refining IC cannot improve the precision, so it's an unhelpful refinement. So we hope our neural network can figure out this. And to implement the pointer analysis in data log, we can implement its core rule as one data log rule, which means that if a variable u can point to an object obj, and there is a data flow from u to v, then the variable v may also point to the object obj. And information about the program under analysis can be represented as facts and rules. For example, the new instruction can be a points to tuple, and the assignment can be considered as a data flow tuple, while the function call can be considered as multiple rules under the insensitive version and the sensitive version. And data log will treat points to facts as vertices and treat those propagation between facts as hyperedges. Those abstraction parameters will be represented as vertices as well. And the data log engine will calculate new tuples based on the rules we mentioned before until it reaches a fixed point. Therefore, selecting different parameters will affect rules applied and then affect the precision and the result of our analysis. Our graph neural network make use of the hypergraphs of data log. But since graph neural networks deal with graphs better, we need to transform hypergraphs into graphs first. Firstly, we replace every hyperedge with bidirectional edges from every head to every tail. And since neural networks need real vectors for calculation, we assign each vertex a feature vector based on its relation name, because relation names are general among different programs. In these programs, we have points to, we have data flow, and in the another program, as long as we are still running pointer analysis, those relation names still exist. So after training the neural network on a program, it can learn how to behave on other programs. So after the transformation, we use a graph neural network to process this graph, which calculates new feature vectors based on the graph structure. Then we use the final feature vectors of parameter vertices to classify whether they are helpful or not. So back to the example. Though the maxset solver cannot distinguish unhelpful parameters, our neural network may say that IC is unhelpful. So we can prune out IC, and the maxset solver will choose either IA or IB, and it will be an effective refinement. So to train our neural network to distinguish helpful refinements, we take the refinement trace and then cancel the refinement one by one. For example, to check whether P1 is helpful, we remove P1 from the last abstraction, which is precise enough to eliminate all false alarms. Since in the new abstraction, all false alarms can still be eliminated, so we can mark P1 as unhelpful. For P2, the abstraction after removing it fails to eliminate one false alarm, so P2 here will be considered helpful. Then we collect those helpful refinements as our training set. To experimentally show the effectiveness of our framework, firstly, we check whether our framework truly improves the scalability of old work. Second, we compared the precision of our approach to a state-of-the-art pointer analysis. Then, we inspect the number of parameters pruned out. Since neural network can make mistakes, we check how often and how much precision loss are there. Lastly, we illustrate that using neural network alone does not work well, so our combination of GNN and maxset solver is necessary. We use two analyses to illustrate our ideas, and we will show the results of the pointer analysis. For the scalability, we select benchmarks that the baseline approach will time out, and we train 3 neural networks using 3 different training sets. Here, blue bars stand for the baseline approach, and other bars stand for our approach. Longer bars here means longer time costs, which is worse. And though our neural network still time out on some benchmarks, the frequency is less. And our neural network terminates on many benchmarks in less than 4 hours. For the number of resolved reports, longer bars means higher precisions. And as the picture shows, our approach resolves more reports than the baseline on almost all benchmarks. And on the benchmark but broad, our approach even achieves a breakthrough of 0. And our overall improvement is over 100%. We also compare the performance of our approach to a state-of-the-art pointer analysis approach. The result shows that our approach can resolve more reports than the pointer analysis approach. but since refinement-based approach tend to be slow, so our approaches are slower than the pointer analysis approach. But this suggests that we could combine those two approaches. For example, we can run the fast pointer analysis first, and then we run the refinement-based approach only on those hard reports. And to figure out why our approach approves such a great improvement, we found that our approach can achieve pruning rates at about 88% to 95%. And for the precision loss, we found that only one of our model has some precision loss, and all of our approaches are faster than the baseline. And to check whether our combination of GNN and MaxSet is necessary, we run the obstruction refinement using neural network alone without MaxSet, and the results are shown as green bars. Its results on most benchmarks are bad, and on some benchmarks, the obstructions are overly precise that even raise out-of-memory exceptions. So this proves that our combination of GNN and MaxSet is necessary, and this combination inherits the strengths of neural network and MaxSet while avoiding their weaknesses. In conclusion, our approach makes use of hypergraphs generated by data log, so it could be applied to different analyses without feature engineering. And then we combine the neural network with the MaxSet solver to determine exact refinements. And that's all for today's present.
All right, we have time for a couple of questions.
Thank you for the talk. I wonder how large your programs were in your training set, and two, how you could determine that alerts were real or spurious, whether that was there was a golden data set for that, or did you have to do some kind of manual process to classify that?
So the first question is how large are our benchmarks, right? Yeah, we choose some small benchmarks from the Dakakpo benchmarks, and we train our neural network on those small benchmarks, and we found that it could generalize well to large programs that are unseen when training. And I'm sorry, I did not get the second question. Oh, it should be hundreds of lines, I think.
Okay, and the second question, did you actually do manual classification of the alerts, or did you have some automated way to do this so you know how to refine automatically, or did you have some human in the loop?
Okay, so we just, so you just asked how we generated the training set, right? Or
For the alarms signaled by the pointer analysis, how did you know whether there were false alarms versus real alarms? Is that?
Okay, so for small benchmarks, like we shown here, since they are small enough, the baseline approach can terminate. And due to the property of obstruction refinement, it will refine the obstruction until it cannot refine the obstruction more. So all false alarms will be resolved on those small benchmarks. But for large benchmarks, since the baseline cannot terminate, it does not promise to resolve all false alarms. So that's why our approach can resolve more reports than the baseline on large benchmarks. Okay.
Very interesting talk, thanks. I know that it's usually a very difficult and a difficult question to ask what a neural network is learning, right? And nobody usually has a very good answer. But here I was curious, what concepts is the neural network learning? How does it know when to suggest a refinement and when not to? Did you do any kind of analysis on what is actually being learned?
So did you ask for whether we have done, whether we have tried to explain what the neural network learns? Okay.
Exactly.
We have tried and we found it learns some complex patterns. We know they may be helpful for program analysis, but it's hard to conclude in neural language in several sentences. But we found those features it learns are quite meaningful. We have done such explanation in our paper. But since there are not conclusions that could be taken away, so we do not show those results there.
Okay, thank you.
Okay, let's thank our speaker again, and then it's time for lunch.
Yes. All right, so we're on to our next speaker. It's Young Chan. He's going to be talking about reasoning about protocols using the CMP abstraction, and I believe a mechanized proof about doing so. So take it away.
Okay.
Oh.
Hello everyone. This is my talk. My name hello. The title of my talk. The title of my talk is mechanizing the CMP abstraction for parameter verification. My name is Yunjian Li. This is a joint work with Bohua Zhang and Jun Pang. This is the outline of our work. First is the breach induction to CMP and our motivations and our contribution, and the syntax and the semantics, and the symmetry, and the guard stringing, and the parameter abstraction in CMP method. And the last two one is the tools and our experiment. The last one is our conclusion and future work. What is CMP? CMP is an abstraction technique for parameterized verification for protocols. As the figure shows, the origin protocol model has n nodes. The right is the abstraction protocol mode. In the abstraction model, only the m nodes in the origin protocol model are returned. And the other nodes from m+1 to n is abstract into a single node and other in the abstraction protocol model. This is the workflow of in CMP abstraction. It is a typical abstraction refinement process. First, we do an initial abstraction and then model checking the abstraction model. If there's a counterexample, we will find a ruler for CMP abstraction refinement. If the ruler exists, we will analyze it by hand, this ruler, the counterexample, and finding auxiliary invariants to strengthen the guard of the law, the guard of R, and then abstract the strengthened ruler, and then make a new abstraction model, and then model checking, and a new round of abstraction refinement. To work out a correct abstraction model, we need rounds of abstraction refinement. This page is a tactile introduction of CMP. Our motivations. Now, formalization of the CMP abstraction is still absent. No formalization of CMP. And most applications of CMP are conducted informally by hand, and it is prone to error. Our contribution is formalizing the CMP in sub-error, and we give us syntax-directed procedures for abstraction and strengthening. And we also implement a tool, AutoCMP, for carrying out CMP. And we also do some case studies, including an industry scale cache coherence protocol, the Stanford Flash protocol. The last one is the syntax and the semantics for specifying a protocol. a protocol, the first one is a constant, the second one is the variable, and then the expression, formula, statement, and a ruler. A protocol is just a pair of initial state and the ruler side. And as usual, we can define reachable states of a protocol instance by inductively, and we can get the concept of reachable state set. And an invariant of a protocol is denoted as follows, meaning that all state in the reachable state satisfy the formula, the invariant formula. We use a simple mutual exclusion protocol to illustrate the above concepts. There are two guided choice rulers. There is the translation rulers of the protocol model, and there's the two formula to specify the initial state, and this is the parameterized protocol, and our requirement or our problem is to prove the invariant, the mutual exclusion invariant hold for the parameterized protocol mode. This formula means that if a node in the critical section, then the other node can't be in the critical section. And now we introduce the symmetry by the actions of permutations. This is the syntax guided definition of the permutations on the constants, variable names, and expressions, formulas, and statements. And we also can define the permutations on states. Based on the definition, we can define the symmetric parameterized formulas, statements, and protocols. If a protocol is symmetric, we can use a lemma of symmetry reduction. Means we can also use the example. The mutual exclusion protocol defined in above is symmetry. By the symmetry reduction, we need if we need prove the parameterized invariant, we only need prove the following: a much simple complete formula. After introducing symmetry, we define the guarded strengthening of a ruler. We define two kinds of strengthening. The first one is simple. We just add a invariant formula. An invariant formula is of the implication formula. We can simply add the formula into the guard of the ruler. This is just this one is simple. The second guard strengthening, we can add the conclusion of the invariant into the guarded of the ruler. If the guard can imply the antecedent of the invariant. We also use the learning example to show if we give this invariant, we can construct a strengthened ruler. The strengthened ruler is this one, STII 等于 is equal E is the original guard of the ruler, and the right one is the strengthened parts added from the conclusion of the auxiliary invariant. and the action is also the same. So after strengthening the ruler, we get a middle ruler or a reference ruler of this strengthened protocol. This one has the same initial specification, and one or two rulers is strengthened by the auxiliary invariant. The most important we can for strengthening we have a correctness lemma. This means that if f is an invariant of the strengthened protocol, then f is also the strength is the invariant of the original protocol. This means the two protocols, the original parameterized protocol and the strengthened one, has the same reachable state. After define strengthening, we can define the abstraction. The CMP abstraction is rather complex. We list three principles. The abstraction should be fine-grained. The abstraction should be syntax guided. And the abstraction should be sound. We use an example to show why how to obtain the three principles. For how to abstract x is not equal to y, if x and y are of Boolean variables, x is not equal to 1 can be directly abstracted into x is not equal to 1. But x1 are of index x. This one should be abstracted into true. We have to make a consecutive abstraction. So different types decide different abstraction result, and especially we should pay attention to the negation of a formula, which we introduce the safe conditions of a formula. This is the abstraction with a simple type system, and we also introduce the safe conditions for abstraction. These are the syntax guided abstraction definitions: abstraction of expressions, abstraction of formulas. Especially if we need to define the abstraction of negation, it must be guaranteed that the formula f is a safe form. This is a safe conditions. When we do abstraction on statements, also we propose the concept of well-formedness of this statement. Our abstraction on statements is only for the well-formed statement. We also define the abstraction of statements. There is also some abstraction rulers. The third one, our abstraction should be sound. The soundness is illustrated by the commutation graph of the abstraction matrix. This means that in the original protocol model, if S is going to S prime, then it is in the counterpart of the abstraction model. The abstraction of S should also reach the abstraction of the state S prime. This is the communicate S to S prime and S to ABS and the ABS to the ABS prime. We also use the long example to show how the abstraction result of the abstraction result of the mutual exclusion protocol. For the four rulers, we use the abstraction of the rulers to function on them and then get the abstraction protocol. The last one, we introduce two kinds of environments. It has in the parameterized model, we use the stringent form, and in the abstraction model, we use an observation formula. The definition is as shown in the definition. It is rather complex. And the last one is the main theorem of the CMP. It proves the soundness of the CMP method. It is quite complex, and we also use the long example to show how we can prove the correctness of the mutual exclusion protocol. We can construct two kinds of auxiliary invariants. They have two versions. The first one is the stringent form for the used in the parameterized model, and the second is for the observation. This is used in the abstraction model. Usually, we observe that the observation invariant is correct in the abstraction model. Then their counterpart, the stringent invariant, is also correct in the original parameterized model. So usually we can use a model check to check the abstraction model. This section is on our implementation of our theory and tool and case studies. First one, we formalization all the theory, and then we develop a tool. This is the framework of our tool. It is combine model checking, abstraction, and theory proving. Our work make the fifth part, the CMP abstraction is for automatically. The three sides is the Isabelle theory. The automatically generated theorem from auto CMP. We also evaluation our tools. It is much automatic than the tools of the state art. We also can prove the flash protocol formally. We have found two mistakes in the previous CMP work of Zhou in Intel. The last one is the conclusion. We think formalization of CMP is quite difficult. It is difficult proposed about 20 years ago. we formalize Isabella we formalize the CMP theory in Isabella for the first time. The future work is we also extending the formalization to handle more complex cache coherence protocol. We also want to link our work with the automatic event finder in the future. That's all. Thanks for your attention.
Thanks for the talk. I was just wondering, do you have any intuition on, in this particular domain, what the challenges for invariant synthesis would be?
I beg your pardon.
Oh, just for this particular problem, what makes finding invariance hard? Relative, especially like, if you could give some contrast with other domains.
Because the formalization of the syntax-guided rule, the formalization is quite difficult because it needs propose many set conditions, such as the safe conditions and the well-formed needs of the statement. We must place the syntax constraint to make the semantic formalized. So I think it is quite
Thank you.
All right. So I'll talk to you about some, yeah, no, yes, okay. I'll talk to you about some work that we did when I visited AWS a while back, which essentially tries to tackle this question, which asks why don't we have formal methods or verification tools in particular integrated into distributed system development? And I argue that to a large extent, this is because researchers and developers have different conflicting desiderata. So on the one hand, we have researchers that typically design powerful reasoning techniques, often for domain-specific languages. Prime examples are Spin, TLA+, and so on. And on the other hand, we have developers that prefer mainstream languages, and they don't care so much about the underlying technique as rather about whether it integrates well with their workflow. Right, so what I argue we need to get verification tools into distributed systems development is techniques that work at the implementation level so that developers do not have to learn new languages, that are fully automated, that offer some API for abstract modeling, and that they also offer some verification guarantees. And in this talk, I'll talk to you about MUST, which is a practical way to do model checking for distributed protocol implementations. MUST is a bounded model checking framework, and the key observation behind it is that protocol implementations typically consist of large, complex parts of local computation sequential code. And then there's just a small handful kind of a code that takes care of inter-process communication. So MUST essentially advocates for this design for a verifier, which has that take a mainstream programming language like Rust or Java, and this will do your local computation, and then have a lean concurrency API through which all inter-process communication will pass. Right, so as long as the code abides by this convention and all the inter-process communication goes through this API, then one can instantiate MUST for a given mainstream language. And in the case of MUST, in this concurrency API, which is where the model checker lives essentially, this is backed up by a declarative semantics, which is very tightly coupled with a dynamic partial reduction algorithm. And in fact, I can show you the API. It's these three operations. We have a non-deterministic choice among a set of values, a send operation, send to thread T the value V, and then a receive operation. And MUST is the first framework of its kind, like a dynamic partial reduction framework that has a number of features that are quite useful in modeling distributed protocols, like non-blocking receives, selective receives, and so on. And I'm going to go over these in the rest of the talk. But my goal is to convince you that this can be a useful tool when dealing with distributed protocols. So let me begin by talking a bit about the underlying formalization of the API. So in MUST, the semantics of a program is given as a set of graphs. And I have an example up there. This program has no local computation, but even if it did, this wouldn't show up in the semantics, right? So we have a thread T1 that sends a value to itself. We have T2 that essentially sends two messages to, whoops. Anyway, so it sends two messages to T3, and T3 just gets one of them. Now, the semantics of this program is a set of graphs. I have two graphs there on the right. The nodes in the graphs correspond to instructions, and then the various edges denote relations between the instructions. So this black edge there means that these two sends are ordered in the same thread. The green edges show which value the receives are getting. This is getting 1. This there is getting 2. So some comments about declarative semantics. The reason why we use declarative semantics is that it's flexible when talking about the underlying communication model. So for example, this graph on the right is inconsistent in some models. If we assume, for example, peer-to-peer communication, then T3 cannot read 2 before reading 1. Right? So this graph is not a part of the semantics under peer-to-peer. It would be a part of the semantics, as in this case here, if we assume, for example, asynchronous communication, UDP and so on. So this is one point. The other point is that this semantics is a partial order semantics. So for example, T1 does not interfere with the other threads. And so in the graphs, this node corresponding to this send over there doesn't interfere with the rest of the graph. There are no edges incoming, outgoing, and so on. And having this partial order semantics is useful because based on it, we can devise a dynamic partial order reduction algorithm. The way this works is that it verifies a given program by enumerating the graphs that are a part of the semantics. And I can show you a very small example. The procedure is essentially a depth-first search. So we start from an empty graph. We execute the program, and we add the instructions one by one. And whenever we're adding a receive, so here we're adding this receive from T3, we explore all possible options for the message that this receive can get. And of course, in this example here, the option above where it gets the value 2 will only be explored if this is allowed by the underlying communication model. So the DPR of MUST is the first DPR for message passing concurrency that is sound, meaning no false positives. It only explores consistent configurations. It is complete. It will explore all the graphs in the program semantics. It is optimal, no redundant work. And it's also parametric in the communication model and has polynomial memory consumption. This parametricity shows up in the API, so we can actually select the communication model under which we send and receive messages. OK. So now let's take a closer look at the features, starting with non-blocking receives. Non-blocking receives are useful when modeling things like timeouts. So for example, if a receive doesn't get a message within some time frame, then it might time out, and we want to be able to model that in our framework. And there are two ways to do this. There's what I call here a naive way, which we can do with the API as I've shown it so far. And then there's what MUST actually does, which requires enriching the API a bit. And I'll explain why MUST doesn't follow this modeling on the left. So I received the timeouts. We wanted to just return bottom when it times out. One way to do this is to use this non-det there. And if it returns 1, we do a blocking receive. If it returns 0, we can return bottom. So MUST does not do this, and instead it kind of changes the API a bit there, and it adds this attribute denoting whether the receive is blocking or non-blocking. And for non-blocking receives, we modify the semantics so that they can return bottom. And if we do this, actually we get a coarser semantics and a coarser model. An example here is this. where we have n threads just doing a non-blocking receive. If we have the naive modeling, then just to model all the combinations of the non-deterministic choice, we have 2 to the n graphs that we would have to explore in our semantics, and the algorithm would have to enumerate all these graphs. But if we have this kind of special modeling, then there's only one graph in the semantics, which is this one. All the reads are just returning bottom. There's no message that they can read from, and we can get away with just one graph. Right? So essentially, another thing that this framework is advocating is that this tight coupling between the semantics and the algorithm, and how to build the semantics that kind of favors verification. And there's a similar story for selective receives. So selective receives are useful for modeling things like versioning, communication closure, and so on. If there's a protocol that you can decompose into different rounds, then a particular round you might want to get just messages designated for that round and not messages for previous or subsequent rounds. One way to do this is with selective receives. Again, 2 ways to do this. What we want is essentially some predicate in our receives saying which messages we should get. Now, the naive way to do this here would be to just do a receive, get the message, and then have some assumed statement that essentially aborts the exploration if the predicate that we care about does not hold for the message that we got. But MUST does not do this, and again, it builds this thing into the semantics. The semantics are aware of predicates. The reason, similar to before, is that this is coarser, and we have an example for that in the paper, but also more expressive. And I want to show you here why it's more expressive, because this is a bit more interesting. In this example, we have 2 threads. The T1 sends 2 messages to T2, and now T2 wants to receive them in the opposite order in which they were sent. But note that this program here is assuming peer-to-peer semantics, right? So if we do the naive modeling, then as soon as we reach this first receive there, and if we follow this modeling, we'll do the receive, but then under this normal peer-to-peer, the only message that this guy can get is this one, and the assume will abort. There's no full non-blocked execution that we'll get. However, if we change the model, and we have the semantic support, then there is one full non-blocked execution that we get, which is this one, which is not expressible with assumes. And we essentially get that execution because we change the meanings of receives under peer-to-peer from, for example, very roughly, fetch me the first message from a given sender that's available to me, to fetch me the message from a given sender that's available to me and satisfies the predicate that I care about. And this is how languages like Erlang, if you've seen programs in Erlang, do this sort of receiving based on some clauses that they have. Okay, so again, the story here is that we modify the semantics. We make our receive statement like this, and if we want normal receives, like the way I showed them previously, we just make the predicate be true always. And the kind of final 2 features I'd like to discuss, which are related, they have to do with how DPOR works. And the issue is that DPOR typically only reasons about assertion safety for a given program. So it will just ensure that no assertion in the code is violated. But often, especially in this context, it is useful to talk about properties that somehow describe the state of the whole system. And I have a kind of a small example that tries to get this point across, which is just 2 threads sending some message to some other thread, doesn't matter which one, and we ask something like, is the send of T1 always executed before that of T2, which is somewhat non-trivial to express an assertion. And so MUST wants to be able to reason about such properties, and the way that this is done is by employing monitors, which are just some special threads that track communication in the system. And so in this case, if we want to reason about a property like this one, we would transform this program into something like this, where instead of just doing a send, we do a send notify, we notify TM. This is a monitor thread. And the monitor just gets 2 messages and checks whether the first one is the one sent from T1 to Tn, and the second one, the message sent from T2 to Tn. this property here that we care about does not hold clearly, but the point is that by having monitors kind of track this communication, we can reason about this thing. And now, so this is one kind of point. The other point that I want to stress is that if we look a bit under the hood and how these send notifies are implemented, these are just another send to the monitor, right? So this thread notifies the monitor about the subsequent action, and this one does the same thing there. But what's important is that this communication with the monitor needs to take place under a different model than the rest of the system. We kind of describe in the paper why that is. Very roughly, it's because if two notifications to the monitor are causally related, then we need to ensure that they'll arrive to the monitor in the correct order. And for this, we need a different semantics for the messages that are sent to the monitor. But this is actually possible in Must, and we can have multiple communication models coexisting within the same program, and not just causal delivery and peer-to-peer, but also asynchronous communication, mailbox, and so on. You can mix and match within a given program. Okay, and then I'd like to kind of end with some note on the practicality of this. So this is some case study that, again, was done in the context of AWS. We tried a handful of realistic protocols, and some of them were designed along with developer teams. And I just have two benchmarks here to make 2 points. The first point is that if we have selective receives, we can see in this benchmark, it's the state space is exponentially smaller, so it does help, and it's kind of beneficial for both for modeling, but also for verification purposes. And the other one is that even though monitors increase the amount of messages that are sent in the system, they do not increase the state space exponentially. They increase it just a bit, but it's still manageable. Right, so hopefully I convinced you that this is a useful framework, and I'm very happy to take your questions and feedback.
All right, if anyone has any questions, step up to the mic. Now is your chance. Okay, maybe I can try and get something kicked off here. So one thing that I was wondering is how do you actually build these models? Are you dynamically executing the program and constructing the model on the side and then model checking that? Or is this a static process and then you do model checking on?
You mean as in how do we do the verification essentially? Or?
Yeah.
Yeah, so it's a dynamic thing. You repeatedly execute the program. Maybe I can go back to this example in the beginning. So this exploration. So what you do is that you execute the program one instruction at a time, right? So you execute this, you make this in your graph. So you make the graph bigger. Whenever you have a choice, like here, for example, there is a choice. You go with one of them and keep executing. And then when you finish completely dynamically executing the program, then you restrict the graph. So you would get, like if you end up with this state, you would restrict it to this thing. You have some marker that you have some work to do. And then you use the restricted graph as some guidance for the runtime and re-execute the program from the beginning. And then try the alternative option to see what happens. So essentially this guidance part, if you have receives in this cut graph, then the model checker informs the runtime of the value that this receive should be reading.
Gotcha. And so you're actually model checking like LTL properties, or what's going on under the hood there?
No, there's no LTL. The properties that are expressed, for example, with these monitors are as special processes that kind of track what you want.
I got you. And so like a verification failure would be one of those monitors sort of.
Right, exactly. Yeah, exactly.
Yeah, makes complete sense.
So how does this work with the non-determinism in the local computation part, which might affect which messages are sent and so on? Do you assume every non-det thing calls your...
Yes. So the dynamic partial reduction kind of by default assumes that there is no data non-determinism. If there is, then, which we have in this framework, it needs to go through this API. Yeah.
Can you pull up the slide where you talk about how you're exponentially shorter than other approaches? Yes,
this one,
the naive versus must.
Yeah.
So I didn't fully understand why allowing it to provide to return bottom in the way that must does it is different. And can you say a little bit more about that?
Right. So the point is how many graphs you have in your semantics, and if you have this non-det, then this, I don't have the graph here, but this will show up in the graphs.
I understand why the non-det has 2 to the n,
Okay.
right? What I don't understand is why the same example in your system only has 1.
Right. So there's no non-det, right? So it's just that you treat this thing as a built-in, and there's like some attribute that says that this is non-blocking. And so if you had an exploration like this one here, so here for each of the sends from which you can read, right? You try there's a different graph, and then you would add to all these sends a bottom option, right? So it's just some like some special node. You can imagine some special node in the graph from which non-blocking receives can read. But in this example here, since there is no send, there is no nothing, right? The only message that these receives can get is bottom. So it's just that there is only one consistent graph in the semantics, and this is what you explore.
Oh, okay. I guess, right. So this is under the condition where there's no sends.
Yeah, if there is a send, then you'll also explore, this receives reading from that send.
If I have n sends, then I'll still get multiple.
Yes, yes.
Although maybe I would get n if I had n sends and
if you have n sends, well, to which process are the sending the message?
To the one that's receiving.
Because here I have multiple ones, right? Multiple parallel processes that do the receive. If you have a single process that's receiving n messages, and there are n different ones, for example, that send, then you may have even like quadratic, whatever. Yes, n options for the first one.
I see. So you can get 2 to the n if the graph is just this way, but the point is you can optimize it if you don't have.
Yes. So you just
situation.
optimize in some cases. Yes.
Yeah. Okay. Thank you.
Let's thank our speaker again. So our next speaker is Nikhil from Princeton, and he's going to be talking about an approach to procedure summary using vector addition systems and inductive potential.
Volume for everyone in the back. All right. Hello, everyone. My name is Nikhil Pimpalkari. I'm coming from Princeton University, and I'm going to be presenting my work with Zachary Kincaid. The title of this talk is also an outline of this talk. And so what I'm going to be talking about today is what problem I solve, monotone procedure summarization, and then I'm going to talk about how I solve it with vector addition systems and inductive potentials. Here is a summary of what I'm about to say. Existing verification techniques are based on heuristics and can behave counterintuitively, and so let's build new ones formally guaranteeing predictability. So probably all of you are familiar with the program verification setting, where you have a program like this one, the details aren't important, and you have a specification like this one, which says that this add function actually computes the addition of its inputs. We have some state-of-the-art verifiers like Korn and Ultimate Atomizer that, given these two, say, yes, this program meets this specification. These two tools are model checkers, and what model checkers often do, given a program, is that they compute an over-approximate summary of what each procedure's semantics, and they use this summary in order to interpret procedure calls. And then they do a counterexample guided loop in order to prove or refute a property about the program. But this is not a talk about model checking. This is a talk about procedure summarization. So I only care about this component, the process of computing an over-approximate summary of each procedure's semantics. I'll comment that procedure summarization has clients beyond program verification, but in this talk, I'll only be talking about verification. All right, so we have a software verification competition, and according to this competition, these are the best verifiers to use when you have a recursive program. But these tools display some counterintuitive behavior on related queries. So they both succeed in showing that this program meets this specification, but what if we considered a different specification? So this specification says that the add function is increasing in the second input. A question: which specification should be easier to prove about this program? One answer for that is that the blue one should be easier, because the red property implied the blue property. The red property is a stronger description of program semantics, and so it should be harder to prove for this program. Well, unfortunately, Korn and Ultimate Atomizer don't agree with this intuition. They succeed in proving the red specification for this program, but they fail in showing they fail to produce an answer when given this blue specification. And so they behave a little bit counterintuitively on related specifications, and they also behave counterintuitively on related programs. Consider these programs. These programs are both recursive programs, and they only differ in the conditional guarding the base case. The red program on the left has a non-deterministic guard. So every time the conditional is hit, it arbitrarily chooses true or false. And the blue program has an n less than or equal to 1. So a question, which program should it be easier to prove specifications about, the red program or the blue program? One answer is that the blue program should be easier because it's a refinement of the red. Every execution of the blue program is an execution of the red program. And so if I prove something about the red program, then I'm proving it about more executions. Proving it about more executions should be harder. But again, Korn and UAtomizer do not agree with this intuition. So the core reason for this unpredictability is that the state of the art in procedure summarization is driven by heuristics. And so it's difficult to predict how the procedure summarizer is going to work on related queries because they may interact with these heuristics differently. So the goal of my work is to develop a predictable procedure summarizer in the sense that it is compositional and monotone. A compositional procedure summarizer will compute the summary of a procedure from the combination of its parts and will allow us to reason about the effectiveness of the summarization technique on composite programs. And a monotone procedure summarizer will compute at least as strong of a procedure summary for a refinement of a program as for the program itself. And so this will give us a way to reason about the effectiveness of the technique on related programs. For the rest of the talk, I'm going to show you my monotone procedure summarization technique working on this verification task. This verification task involves an integer model of a program which accesses memory. And I'm trying to bound the number of times that it accesses memory. Imagine a program that traverses a binary tree. And at each node, it saves the value of the node to a buffer. And at each leaf, it writes everything in its buffer to memory and clears out the buffer. This program is an integer model of such a program in which size represents the size of the binary tree, buff represents the length of the buffer, and writes counts the number of times that we write to memory. So at every node, we increase the length of buff because we need to add the current node into our buffer. And at every leaf, we make buff writes, and then we reset the length of our buffer to be 0. I'm going to show you how I compute a procedure summary of this procedure in a monotone way that is strong enough to show that the number of writes that this program makes is bounded by the size of the tree. So a rational vector addition system with resets is just a program in which all of the variable assignments are of a particular form. And so I'm going to compute procedure summaries in a monotone way by computing the best Vassar abstraction of a program and precisely computing its dynamics. So first, I'll formalize what I mean when I say best abstraction. Given a program, I want to compute a Vassar program and a simulation function f, such that for every pair of states which transition to each other along the program, the image of these states under the simulation function f transition to each other in the Vassar program. In prior work, Silverman and Kincaid computed the Vassar abstraction of the body of a while loop. And then they computed the set of states that this Vassar could reach over an arbitrary number of transitions. And then they took the inverse image of this set under the simulation function f, and they got an over-approximation of the set of states that the while loop could reach over an arbitrary number of iterations. In other words, a loop invariant. Now, what I am doing is that I'm computing a Vassar abstraction of the body of a procedure. And then I'm computing the reachable set of states of this Vassar along transition sequences corresponding to the recursive structure of the procedure. The language L of such transition sequences is a context-free language. And so I'm going to be computing the context-free language reachability of Vassar. Then, like before, I take the inverse image of this set under the simulation function f, and I end up with an over-approximation of the set of reachable program states along arbitrary executions of the procedure. In other words, a procedure summary. Now, I don't compute any Vassar abstraction. I compute the best one, which is called the Vassar reflection. The Vassar reflection of a program has the property that for any other Vassar abstraction of the program, there exists a simulation from the Vassar reflection to the other Vassar abstraction. Simulation can be thought of as a loss of precision. And so the Vassar reflection is going to lose some precision compared to the program, but any other Vassar abstraction is going to lose precision compared to the Vassar reflection. So the Vassar reflection is best because it captures as much about program semantics as any Vassar abstraction. I keep saying Vassar. What is a Vassar? A Vassar is a program in which all of the variable assignments are of the form variable equals constant or variable equals variable plus constant. And I'm going to be computing Vassar abstractions which linearly simulate the program. This means that the f function on the previous slide is going to be a linear function. And in simple terms, this means that the variables of the Vassar represent linear combinations of variables of the program. And so my first contribution is an algorithm to compute the Vassar reflection of a program, which linearly simulates any other Vassar abstraction and is therefore best because it captures the most about program semantics of any Vassar abstraction. So here is our running example, and here is its Vassar reflection. The Vassar reflection has two variables, a and b. A represents buff, and b represents buff plus writes. The program assignment buff plus equals 1 gets translated to a equals a plus 1, and b equals b plus 1. And the combination of commands writes plus equals buff and buff equals 0 gets translated to a equals 0 and b equals b, because the new value of writes gets the old value of writes plus the old value of buff, and the new value of buff is 0, and so the term buff plus writes remains constant. The key contribution of my work is that we can compute the CFL reachability of Vassar. So for this Vassar, we can conclude that after any execution, we know that the a variable is going to be 0, and the b variable is going to be some non-negative k, where k represents the number of times that the tree count function is symbolically recursively called. I'll say a few comments on this contribution for the experts in the room. The way that we did this is that we compute the Peric image of an expanded version of the grammar of the context-free language. And this object contains enough information to compute the possible net effects of the Vassar along any transition sequence inside of the language. So given our exact summary of how the Vassar works, we replace the a's with buff and the b's with buff plus writes, and we have an over-approximate summary of the semantics of the program. Now, I've presented everything here in terms of Vassar, but this also works in terms of lossy Vassar, which is a relaxation of Vassar to inequalities. Lossy Vassar is better than Vassar because every Vassar assignment can be viewed as a less than or equal to and a greater than or equal to. And the lossy Vassar can abstract additional information about the program, like the fact that x is less than or equal to 0, that the Vassar cannot. All right, so using Vassar-based summarization, we were able to compute an over-approximate summary of the semantics of this program. But this over-approximate summary is not yet strong enough to prove the property that we wanted to. The core reason for this is that the Vassar is losing information about the maximum number of times that the tree count function can be recursively called as a function of the input. And so the way that we're going to refine this summary is that we're going to synthesize bounds on the number of times tree count can be recursively called, and we're going to apply them to this k variable. And in doing so, we're going to strengthen the summary enough to be able to prove this property. We synthesize these bounds with inductive potentials. So we compute a refined summary in a monotone way by computing a potentially infinite set of bounds on recursive call count and applying all of them to our summary. So we search for bounds on recursive call count of this form, where the x's are program variables and the a's are constant coefficients. In order to synthesize and apply bounds in a monotone way, at a high level, we compute a polyhedra, pictured here, such that every point in this polyhedra is an assignment to the a coefficients that would be a bound on recursive depth for all possible inputs. And then we use polyhedral techniques in order to finitely encode the bounds associated with all points in this polyhedra into our summary formula. When we apply this refinement to our previous summary, we now see that k is bounded to be less than this term. And our overall summary is now strong enough to prove the property that we wanted it to. All right, so I implemented this technique, and we evaluated it on the recursive category of the software verification competition. But this benchmark has some weaknesses as a evaluation setting for procedure summarizer. One issue is that it contains a lot of programs which are difficult for procedure summarization, like the Fibonacci function or the Ackermann function, but checks properties about them that can be checked via execution, like checking that the Fibonacci of 7 is equal to 13. Another problem is that there are many copies of tasks that involve the identity function, the Fibonacci function, and the addition function, and so there's low task diversity. And so our final contribution is a benchmark of diverse recursive programs, and none of these tasks can be solved via execution. Here are the results of our evaluation. Recursive and recursive simple are the recursive category within SVComp, and our new benchmark task is called Rec Supreme. On the left-hand side, the red tools are procedure summarizers, the blue tools are model checkers, and the tools labeled M are guaranteed to be monotone. From this evaluation, we can conclude that our tool, LIP, represents a step forward in procedure summarization, and that in some settings, it is even competitive with model checkers. When you have two techniques for monotone procedure summarization, you can use them both on the same procedure and then conjoin the resulting summaries, and the overall aggregate procedure summarizer is also guaranteed to be monotone. So we did this with LIP and compositional recurrence analysis, and their aggregate procedure summarizer is also guaranteed to be monotone, and it's strong enough to solve some tasks that neither one of these tools can solve individually. So thank you all for listening to my talk. Today you heard about a new technique for procedure summarization, which is predictable by being compositional and monotone. Here are the key technical contributions of my work, and thank you again.
Okay, we have time for questions. Just step up to the microphone.
Thank you so much for the talk. So I just wanted to get a better sense of what kind of properties can be improved using this abstraction. So like when you get the best Vassar abstraction, what kind of properties are you checking against it? Like, can it have like quantifiers or?
So the property that you want to check about the overall flow of these procedure summarizers in verification is that you compute the summary and then you check if the summary implies a particular value. And so I don't know off the top of the head what the quantifier situation is in the properties that we checked, but if the procedure summary is strong enough to imply that property, then you would be able to prove it with this technique.
I see. And then to check that the abstraction satisfies the property, like do you use like some like SMT solvers or is it like?
Yes, we make a query to Z3.
Okay, gotcha. Thank you.
Hi, thanks for the talk. This was presented well enough for me to ask a question. So your motivation was predictability, but I couldn't quite tell how you were actually evaluating whether your end result was more predictable than previous tools. How exactly are you evaluating that element of it?
So in terms of predictability, by formally guaranteeing this monotonicity property, we argue that in practice it's going to be more predictable than other tools. And then also in this Rec Supreme benchmark set, we have a couple of, for each program, there's a couple of different specifications that we try, usually of decreasing strength. And so UAutomizer and Korn have this thing where sometimes they fail to prove a weaker specification, and our monotonicity guarantee allows us to solve all of them.
Got it. So in this context, anything that's monotone is predictable for the context of this?
Yes.
Gotcha. So I guess the other competing tools like the CRA or I guess it's only CRA, right? Because you're combining it with lib. Like that one is also predictable.
Yes, that one is also predictable in this one.
Okay, thanks.
Hi, thank you for the nice talk. So my question is, the two motivating examples that you've had, it seems to me that the difference between the programs and specs that Korn and UAutomizer can prove versus not is that there exists some conditional branching that they could not handle, which I assume is very nicely handled by VAS because this is abstracted as non-determinism. So are the examples that you're able to solve and UAutomizer and Korn fail on mainly these examples where some problematic conditional branchings are abstracted? Are there also some other examples that basically you could handle and they could not?
So I think the paper is the best place to look for the examples where we succeed and Korn and UAutomizer fail. But I think that there are cases in which, in particular when we're using lossy Vassar, where we are able to abstract the conditional. And even with that, we still are able to prove.
So you get another conditional and still, am I understanding this correctly?
We are still able to abstract information from the conditional.
All right. Maybe I'll look at the paper.
Okay.
Thanks.
Let's thank Nikhil again. So that was our last speaker. It's time for coffee, so go get caffeinated.
Okay, welcome everyone to our session on gradual typing and other type system related things. And it's my pleasure to introduce Zachary Palmer, who is going to start by talking about intentional functions.
Check 1, 2. Yeah, all right. Hi, good afternoon. Yeah, so I'm Zach. This is joint work with Wes, who's at STI Semiconductor and who was at Microsoft Research when we worked on this together. It's also joint work with Earl, who gave a talk yesterday on completely unrelated research. And I'm going to be talking to you about intentional functions. That is not a typo. It is spelled with an S. Today, when I'm saying intentional function, what I mean is a function that, in addition to being callable, has other behavior associated with it. Okay? So there's some precedent for this. Andrew Appel had an extended abstract in 1995 proposing an intentional equality operator that's meant to determine whether or not two continuations are the same continuation, right? Also, you can think of, as another example, projects like Cloud Haskell and Scala Spores as an example of intentional serialization, right? In addition to calling a function, you can serialize it, transmit it to another runtime, and call it over there. So behavior more than just calling the function. I want to generalize this today because I have a particular motivation that drives me nuts, is that I keep finding reasons to calculate deductive closures. And in those deductive closures, I want to deduplicate continuations, right? And oftentimes, I represent continuations as functions. And I would like to ask if two functions are the same or compare them or what have you. So I'm going to be talking about intentional functions, which is a language feature that we added to a proof of concept implementation of GHC in order to address that problem. And because it's GHC, I'm also going to be talking about something that we're calling an intentional monad, which is the natural consequence of re-encoding monads using this type of function. All right, I'll wrap up and take questions at the end. I'm going to start by talking about that motivation of mine, the thing that drives me nuts all the time. Computing deductive closure is probably something that you're generally familiar with. Just to set the stage, I have a set of facts. I have a set of deductive closure rules. I would like to plug into that set of deductive closure rules every fact that I have that fits in all of the places that it fits in order to see whether or not I can reach a conclusion. And once I've reached a conclusion, well, I add it to my set of facts, and then I propagate it through as well. And I keep doing this until I run out of combinations, and then look, closed set of facts, right? One thing about this process is that when I when I close over these things, sometimes I learn the same fact in two different ways. But since I'm after a set, knowledge is idempotent, right? It doesn't matter if I learn something once or 100 times, I still know it. So in terms of my computation, I can deduplicate that. I see I've learned this before. The second time I pick it up, I go, oh, I already know about that, right? I set it aside. I don't bother doing any additional computation because I found that second proof, because that doesn't matter to me in this domain. This is all standard stuff, yeah? It's interesting to observe that you might also wind up having these sorts of duplicate computational trees. Depending on your domain, this happens more or less frequently. We were working on a project where this was very, very dense, right? Where it was not that uncommon to have two partially specialized versions of a closure rule that were, for whatever reason, provably equivalent. And at this point, what I'm saying is that no matter which third fact I plug in for that third premise, both of these things will give me the same answer. So I don't want to compute the whole tree and have to find a bunch of duplicate facts at the leaves. I want to say, OK, I deduplicate that, right? Save me the work. So I don't just want to deduplicate facts. I also want to deduplicate these computations that I have in progress to save myself the effort of getting the answer to the question, right? Here's a concrete example of what I'm talking about. Three-premise deductive closure rule with two different forms of fact matching the previous picture. If you're very fast and very much in the know, that is CKY parsing written as a deductive closure rule. And if I wanted to implement this in Haskell, I would start by writing a couple of data types to represent whatever information my fact carried around with it. And then I could write this deductive closure rule as a function that starts by taking the two facts that I would like to satisfy the two premises I started with, right? I satisfy those things because this is a programming language and not like an actual closure engine. I'm implementing all of that. I have to check to make sure those variables match. And if they don't, well, that means that these facts don't actually satisfy the rule, right? They don't actually apply. But if they do, then I'll wait for my third thing, right? Once I get the third thing, then I'll check the meta variables again. If these values match up, then lo and behold, I've learned something. Good for me, right? I presumably have some sort of engine that's pumping this thing with each of the different combinations. And I'm not going to put that up on the slide. But whatever type signature I have associated with this, the engine is taking functions that look like that and just feeding them all of the combinations it can come up with. So once I've got this code, let's think about what it looks like when that engine calls this thing. I might call it with these 3 arguments, yeah? And when I do substitution and reduction, I wind up with something that looks like that. Yay, I learned a thing. And that first kind of duplication I was talking about of facts can be witnessed when maybe I've got a set of other facts that I know. This in CKY parsing would be like a ambiguous parse, right? If I substitute and reduce, I get the same thing. Look, I've already learned this before, so I don't push this back through the engine, right? I've seen this thing before. It's in my set of knowledge. I don't try to build another tree out of that. I can just ignore it. But this is a degenerate observation of a broader thing, like a degenerate version of a broader observation we can make, which is that if I throw away that third argument, these 2 sub-expressions, when substituted and reduced, produce the same result, the same function, the same continuation on my computation, right? They're really just that chunk of code with several of the variables replaced with particular values. And so what I want to do is say, hey, are these equal, right? So that if I find out they are, I can throw one away and not have to do that whole subtree of work. Of course, the catch is this is a function. And I'm not allowed to ask that question because blah, 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 theory of computation, yeah? Like, it's a problem because if I can actually answer that question precisely, then I've broken a lot of things. So the reason that I'm talking about all of this is because I found this to be very frustrating. I can respect that asking if 2 functions are equal is not a problem I can solve in this language, but I also get really irritated because I know what's in the language runtime, right? This isn't what's in the language runtime. A closure is what's in the language runtime. And in this case, that closure, a pointer and all of the values of the variables that have been captured, those are equal. And so I should be able to argue to myself, these are going to do the same thing. But the abstractions of the language prevent me from being able to do that. So the summary of my problem is that I have these continuations encoded as functions. And I want to be able to deduplicate the continuations. So that means I'm going to need to ask whether or not those continuations, those functions, are equal. And worse than that, I need to be able to ask how they compare and how they hash, right? Because I need to be able to put them in a data structure and then ask if they're there, right? If there's an equivalent value in that. Fortunately, when you actually write code that looks like this, you don't like write the same thing in several different places. I don't actually need to know if 2 functions are equal. Because if they are, it's almost certainly because they came from the same place in my program, right? And so in this case, I don't need to know whether they're equal. I need to approximate conservatively whether they're equal on the basis of that runtime representation, the closure that I know is already in the language runtime. Okay? And I don't want to just solve equality and sorting and hashing, because this is my frustration, but you might have your own. Right? Somebody else might have their pet project where they go, well, I want to know the following thing about this closure. And so we should be able to generalize this idea. Now, before I talk about how we do that, I do want to mention defunctionalization is a way you'd solve this, right? Instead of representing your continuation as a function, maybe represent it as a first-order data structure. And then you can write whatever code around that data structure you feel like. I've done this a lot. I've gotten really tired of doing this because it's very effective, but it's also really clunky, right? The code you wind up with at the end is harder to read. It's easy to make a mistake when you manually defunctionalize. I don't want to have to do that. I want the system to do some of this work for me. And so the way I'm going to make that happen is by writing functions that look like this. This is an intentional function in our Haskell extension. Again, proof of concept. I don't want to oversell that. This is an intentional version of the standard library function const, which takes 2 arguments and then returns the value of the first one. And when I say this is intentional, what I mean is it's got this position here for a constraint function. A constraint function is a thing that makes an assertion about a type. In the case of eq, it's saying, give me a type, and I will assert that that type has a definition of equality associated with it. So when I attach this constraint function to that intentional function, what I'm saying is that every value captured in the closure of that intentional function has to conform to it. This x, which is free in that sub-expression, has to be of a type that is equable. And you can see that I've got up here on the type signature that assertion. So that way you can't call this with something that isn't itself associated with the definition of equality, right? So once I do that, the type checker will let me have this conforming type b %eq a, an intentional function from b onto a, where everything captured in closure is eq. What can I do with that? We have 3 destructors. The first one is application, because it wouldn't be much of a function if you couldn't call it, right? But I've got 2 more for you. One of them is identify, which asks for an ID associated with the function. The function's ID is going to be its definition site. Think like just the program point where you wrote the function. And the second part is going to be inspect. This is the other chunk of your closure, right? This is going to be the environment of values captured by the closure over this function. Here, you'll notice it's not just the values. I have this existential because I know that everything in this closure conforms to the constraint function. So it's the values together with a proof that every one of the values is, in this example, equatable, right? Once I have these things, I can start writing code for the functions themselves. So if I have a function from A on to B which is equable, right, which has that constraint function eq associated with it, then I can say these two instances of that type are the same if they are defined at the same place and they have all of the same values captured in the environment, right? The closure captures the same environment of values. And again, this is a conservative approximation. 2 functions could be equal, and this would still say false, because they do the same thing, but they're defined in different places. I just don't need that, right? And the nice thing about the constraint function being a parameter is pick whichever one you like, right? Here's a definition of sorting these things, so you can put them like a tree set or something. So what I'm saying is we're using this runtime definition of what a function looks like in order to make that definition transparent to the programmer. In this language, we're representing partially applied functions as these closures. And so I'm just making those closures transparent, making them accessible to the programmer so they can use that information to define whatever kind of behavior they need. OK? We have a formalization of this as a little lambda calculus. Lambda ITS includes intentional functions and a whole bunch of other stuff because we wanted to make the case that they were actually useful for something. It does not include extensional functions because we didn't need them, right? So that means that every function associated, like in this lambda calculus, is associated with both an ID and its environment explicitly, as well as the body expression, which is still undergoing traditional substitution. Okay? We have a proof of soundness. It works by encoding down to an extensional language with GADTs that is itself sound, right? So the soundness comes out of an encoding. But more interesting to me is this property we were calling closure consistency, which is that if you have 2 of these functions that have IDs and environments that match, their body expressions will also match. They will be syntactically identical. And this is the basis on which we can argue the correctness of that conservative approximation. OK? One other quick point, eta equivalence doesn't hold anymore, which I guess isn't that surprising, right? Because I just added more destructors for functions, so you could probably tell things apart a little bit more easily. In particular, when you eta convert, you introduce a new program, like a new lambda definition site. It's going to be a different ID. And so these don't look equal to that conservative approximation. If you restrict to just application, of course, you still have eta equivalence. But we're not restricted there. We have these 2 additional destructors that allows us to tell these 2 functions apart. OK? We have this implementation. It's based on GHC 9.2 because it took us a while to get it together, and that was what was fresh at the time. It works by encoding to GADTs the same way the proof of soundness does, so it is not fast. If we wanted to actually make this thing like industry ready, it would take a lot more like deep exploration of the compiler because we'd have to integrate these destructors with the actual runtime representation. Right now, we're doing this wrapper encoding thing. But using this proof of concept implementation, we can take that code that I had up here before. And remember how I was saying I just want to be able to take that function and put it in a set or something, see if I've seen it before? I can just slap %ord on all this. And lo and behold, as long as everything captured in the closure of all of these functions is comparable, now I can ask whether or not these 2 things like are equal, how they compare to each other. I can put them in like a tree set. I'm good to go. One last point I want to make about all of this. That's not the code you'd write if you were actually writing a deductive closure in Haskell. Like taking a step back from intentional functions for just a second, if I were writing a deductive closure in Haskell, I'd write it as a monad, right? Like I have some do syntax. I like this code better because if you're familiar with do syntax, this is faster to write. It's certainly faster for me to read. I think I can pick the deductive closure rule I had up previously straight out of this code. I mean, I probably wouldn't write it with guards, right? The guards are like a linear search. And so I'd probably have some sort of indexing functions. This is what I'd prefer to write, though, as a Haskell programmer, right? Speaking just for myself. The thing is, if you desugar this, you can see that that function right there is the one that I want to deduplicate. And it's still a function. So if I just go through here and turn these all intentional, suddenly I don't have this problem anymore. The thing I need to deduplicate has a %ord associated with it. I can ask if I've seen it before. I can check it whether or not it's in a set. I can put it in a set, etc. And of course, I don't want to look at this, so we're going to hide it behind our own form of do-sugar. But the general idea is that now we have this intentional monadic environment in which you can write computations that conform to constraint functions. Computations that, in addition to being evaluated, can be subjected to operations like compare or hash. Okay? So the broad theme of the work is just that the compiler already knows everything I've just said. Right? The compiler has this information. I just want it to share with me. So that way I can do things efficiently, assuming that the compiler were actually not just a proof of concept. But I can work with the information the compiler already has and not have to do things like manually defunctionalize. Right? Summary. Intentional functions are functions that have operations other than just application. I've been talking about these. You could have your own. Intentional monads are computational environments in which you can write computations that have these properties. Lambda ITS is our formal lambda calculus that gives us a way of arguing the correctness of conservative approximation that I've just been talking about. We have this proof of concept implementation. You can play with it on GitHub if you'd like. Questions, please?
Hello.
Hello.
Very nice talk, thanks. So you're using GADTs in the implementation, so you mean that you're actually defunctionalizing the code?
Yeah, the implementation is basically just doing automated defunctionalization right now. But the observation is that that's just what we did so we could make sure the language feature worked the way we thought it should. You wouldn't actually do that if you wanted to make the compiler go quick.
So you're saying this is slower, but what's the reason it's slower than?
We haven't gotten to break it apart in too much detail, but the conversations that we've had and the tests that we've run point basically to the fact that by using this GADT encoding, we're preventing the compiler from inlining a bunch of things. The GADT encoding is capturing each element of the closure as a single value together with a pointer to the implementation of a thing, like eek or whatever, which prevents it from inlining.
And also, so it's less flexible than it could be, right? Because you have to have a closed world assumption. You have to know all the sites where this function
We
could
need
be
to be
created.
able to produce unique IDs for all of the intentional functions that are running. But those unique IDs are actually generated from the hashes that the Haskell module itself uses to uniquely identify compiled modules. And so strictly speaking, the way that we're getting around that is by doing that thing where you pretend that hashes will never collide, the same way that the compiler that we're already extending does.
Okay.
Yeah.
Cool. Thanks.
Thank you.
Clarification question. Can I bring my own type class to make a constraint?
Absolutely, you can.
OK. Are there any, and there are no lowercase c constraints, I guess, on what that
The
involves?
one limitation I can tell you is that you cannot then write an implementation of our ID data type for your type class unless you have some way of getting your hands on the contents of it. So as long as you can write the definition of your type class for intentional functions using eek and ord and hash and whatever else we provide for the ID type, yeah, you're good to go.
OK. And then if I'm not very imaginative and don't know what other kinds of operations I might want to perform on my intentional functions, other than the ones you demonstrated, what are some common ones that you could think of?
I mean, so far, the only things we've really looked at are the ones I named, eek, ord, hash, and also serialization. Although what does stand out to me is that basically everything else I can come up with requires at least some level of system support for an implementation of that thing. So deserialization requires some kind of runtime support.
Okay, thanks again, Zachary. Next up, Edward Lee will talk about qualifying system F-sub.
Hello, can you guys hear me now? Okay, sorry. So I'll be talking about joint work with my collaborators Yao Yu, Andre, James, Kevin, and Jonathan. Yao Yu's now at EPFL, Andre's my advisor at Waterloo, James was my lab mate, and he's now at Qualcomm, and Kevin's an undergrad that we had help out with this project, and Jonathan's a collaborator and friend at Tübingen. And these are their pictures, so you can see their faces. So what am I going to talk about today? So static type systems classify the values a program reduces to. So here's an example function, 2 lowercase. It takes in a string, and it returns a string. That's really well and good, and let's just prove useful properties about 2 lowercase that are good for making sure your program's correct. But how would we convey that 2 lowercase leaves in unchanged and doesn't blow up my ears? Well, there are 2 options you have here, and hopefully these won't take out your speaker system. You can view it as a property of 2 lowercase, which gives you down a whole line of work down co-effect systems, which are really cool, which we cited, which I think started from Patrick Sick in 2014, or as a property of n, the variable itself, which draws from a long line of work starting from Foster's 99 PLDI paper on type qualifiers. As you might have guessed, given the name of this talk is about option 2. So we can throw on a type qualifier on top of string, like const, to say that, hey, 2 lowercase takes in a string, but it takes in a const string, so it won't mutate its arguments. Type qualifiers have been used to model a whole bunch of extensions to existing type systems. The one we saw here was immutability, const. There's also exception safety, which most famously, I guess, comes up, no except from modern C++. Nullability in various forms, like in non-null from C#. And there's a whole bunch of work that is done in the checker framework for modeling a whole bunch of extensions, like energy consumption, determinism, you name it. So why do we use type qualifiers? Well, they offer a sound, a pretty mathematically principled, and lightweight mechanism to extend an existing type system. Qualifiers, as Foster pointed out, you can take them from, they have this nice lattice structure, so you can take your qualifiers from some lattice. For really simple qualifiers like const and non-const, they're just the top and bottom of a 2-point lattice, so that's really handy. You can adapt an existing type system with the lightweight subtyping that you want from type qualifiers by exploiting the order equipped from the qualifier lattice. 2 qualified types are in a subtyping relationship when the qualifiers are ordered properly in the lattice, and the types are in a subtyping relationship. And meets and joins from the lattice allow for some expressitivity. I hope I spelled that right. For example, if you compose 2 functions, like in the qualifier system that deals with exception safety and throwing, well, it throws if either of them or their join union throws. So what's today? Well, type qualifiers themselves are pretty well studied, but polymorphism over type qualifiers is a little less so. And why might you care? Well, let's go back to no except as a qualifier system. Here's intmap. It's intmap because I don't want variables right now. It takes a function f and a list L, and it applies f to each element in L and returns that list. When does intmap throw an exception? Well, intmap throws an exception possibly only when f throws. And you can't use subtyping to relate the contravariant qualifier of throwing on f to the covariant qualifier on intmap. So you have to use a variable here. So you add some qualifier variables. Fine, that's natural. But, okay, easy, sure, or is it? Well, let's look at a more complicated example in compose. Here, you've got 2 functions that operate on ints and return ints. And, well, what is the result of int compose? When does that throw? Well, if we knew what the qualifiers Q and R, whether or not F or G throws, we could fill it in with their union, their lattice join, but they're variables now. So how can we fill them in? Well, ideally, we want to write down the lattice, like the expression Q join R, but that raises a whole bunch of questions, like how does this textual expression Q join R relate to either Q or R? Can we do this without losing the lattice structure that qualifiers give us, which gives us this nice subtyping property? And the answer is, well, yes, there luckily is. As people doing universal algebra would call it, when there's a nice lattice that relates expressions on lattices as a lattice itself, and that's called the free lattice construction. So what's the talk outline going to be? Well, we'll give some definitions that are useful for us, hopefully for the free lattice, and we'll build a couple of systems to show you how you could use the structure. First, in the base system, system F sub q, not very creatively named, for modeling type qualifiers with polymorphism. And also, we're going to exploit F sub q and reuse it as a design recipe for some cases where qualifiers and polymorphism over them will prove useful, such as reference immutability and function coloring. And we'll see how we can re-examine some existing qualifiers systems out there with the structure. So here's a definition of a free lattice. It basically tells you, there's this complicated math definition, but it basically tells you that the free lattice orders lattice expressions by how they're ordered in every lattice. Now, that's not very useful, but it's also kind of a mathematician's, so it's kind of a mathematician's definition. It tells you what the object is, but doesn't really tell you how to use it. So what do we do from that? But there's this nice handy theorem that's kind of folklore, because it's been done a whole bunch of times, that gives a bunch of that defines the ordering relationship on the set of expressions, set of lattice expressions over a set of free variables x that tell you what exactly the free lattice is. And there's like a bunch of rules. They shouldn't look too surprising because they're kind of like what you'd expect for deduction rules for lattice, for order in a lattice would look like. And that's really handy because this is almost exactly set up for natural deduction rules. So we can take these rules and write out really familiar subtyping or subqualification rules for computing when two things are subqualified by each other in the free lattice. So it's almost the same rules except with transitivity modified to allow for bounds on variables because we're working in a variant of system F sub, which has bounds on type variables. For orthogonality, we want bounds on qualifier variables as well too. So what have we seen so far? Well, we've seen how expressions on lattices can be encoded as a lattice themselves, and we can see how the lattice order on the free lattice can be expressed using type inference rules that are really familiar to us. So we can use this to build a base system for that you can reuse as a basis for other systems involving qualifiers and polymorphism, and I'll show you how to do so, they're also in the paper too. So we're going to take to get our base system with type qualifiers, we're going to take system F sub, because it has polymorphism and subtyping, and extend it to support qualifier polymorphism using the free lattice and qualifier and subtyping and counting for the qualifiers, or subqualification. How we're going to do subqualifications, we're going to just use those handy subqualification rules, which encode the lattice rules of the free order. And polymorphism over qualifiers with bounded qualifier variables, same way as you have bounded polymorphism in F sub. And to equip our calculus with some base runtime semantics so you can actually prove meaningful soundness theorems, we're going to tag each value, we're going to tag our values, and we're going to construct them with the qualifier expression they should be qualified with, and we're going to add runtime constructs for checking like assert and upcasting qualifiers accordingly. So you can prove some standard theorems. Those are some standard theorems. What does that buy you? Well, using progress and preservation, you already get that, type programs with type qualifiers won't get stuck. And with the additional runtime constraints for checking and upcasting qualifiers, we get meaningful safety guarantees on how qualifiers are used, which we can use to remix as a basis on a design recipe for some extensions. There are 3 in the paper. For brevity, we'll only do 2. So we're going to start talking about, I'll start by talking about reference immutability. Now, a reference immutability system is a type qualifier system that uses const, except this time const is transitive. When you read a variable when you read a reference out of a const qualified reference, like a reference to a struct or something, you get back a const qualified reference regardless of, what it was before. So we can use the system to deal with polymorphism and reference immutability by, basically using the lattice join to adapt the qualifier on a value read from a cell or a record with a qualifier, whether or not be polymorphic or not, on the outside reference itself. And to give it some meaningful soundness properties, we'll just read the tag, the qualifier tag on the value, to check at runtime whether or not you can write to it. You get some standard theorems, progress and preservation, except this time with stores. What does this buy you? Well, it gives you that well-typed programs won't crash right into a const qualified reference cell. That's immutability safety for free. And with a little bit more work, you can show that qualifiers don't really affect reduction otherwise. So like you can erase the qualifiers and still get the same behavior, which is really nice. Another application which we examined, a case study, was function coloring. And function coloring shows up in many forms. Today we're going to like async or await or throws and no accept. Today, like we're just going to talk about colors for simplicity. 2 colors, red and blue. Red functions can call blue functions, but not vice versa. And like red functions in this case can represent async or throws, and blue no accept or sync. As we observed earlier when we talked about compose, we often want to take the join or the union of 2 colors when dealing with like higher order functions. So this is a useful application. So we'll extend system F sub q to model this by modifying the operational semantics to check the colors before allowing a call to proceed, and the typing rules to propagate colors or qualifiers in an effect context. The details of this are all done in the paper because there's a lot of typing rules and we don't have that much time. But you get some standard theorems that tell you that, hey, progress and preservation all hold. And what does that buy you? You get that a red function is never called above a blue function during evaluation, just from progress and preservation, with how the typing and evaluation rules are set up with this nice general framework. So what about other qualifier systems? Well, so the work that we presented today was kind of came out of a bunch of discussions we had with some collaborators of Jonathan and I's at EPFL. Alex, I don't think he's in the room right now, but we were working on the system for tracking the variables captured or captured by a value for doing some sort of effect safety, for doing an effect safety system, which I think they presented as a TOPLAS presentation at POPL this year. And there's been some really related work that Sung Lin is going to talk about today on polymorphic reachability types, which is coming up soon, so stay for that talk. Now, and there's actually some other sort of related work that's kind of surprising that uses the same ideas as capture tracking, except with method names for tracking effects by using method names as a proxy for the effects they call, done by Gariano et al. In the 2019 Onwards paper. So what do they all share in common? Well, when we designed capture tracking, we had these sets of capture variables. We really couldn't figure them out, and we had these ad hoc formalisms for dealing with these sets that qualified our types, and their bounds and transitivity and whatnot. And so did Song Lin, and so did Gary Hano. But if you think a little bit about it, sets are just lattices without intersection, and you can view like sets with union, and all these calculi, since they don't have intersection, you can view their set expressions as just, lattice expressions on the singletons involving the singleton sets on the joins of all their variables for singletons. There's a lot more cool ideas that Song Lin will present about freshness, which we won't get into, but for a lot of the stuff that we did and that relates all of this is that, you can actually recast all of those rules, a lot of those rules, using this little handy bit of universal algebra and some subset of the sub-qualification rules I presented. Just since there's no intersection in those systems, just get rid of those rules. So what are the takeaways? Well, hopefully you can see how you can use free lattices to nicely encode polymorphism for qualifiers. Hopefully our base calculi gives you an inspiration to design your own calculi if you need to use type qualifiers with polymorphism. We've got a bunch of case studies in the paper which might help you there. And hopefully we've re-examined some recent qualifier systems to see how they fit in this framework. So thanks for your time. Are there any questions?
Okay, if there are any questions, then
Thanks for the talk. This is really cool. I would love to see if this can encode tables type system for tables.
Tables.
Like TypeScript has a key of operator,
Okay.
which says I have a type coming in, I don't know what it is, but it's going to be a key for this object, which is my other argument. And this works because key of makes sense for everything in JavaScript because everything is an object.
Right, right.
I don't want to live in that world.
You don't want to live in that world. So I think there's some, I think you might, like, yes and no. Well, I think possibly. I think there's some there's some closely related work that Magnus Madsen's doing on using things that are really related to lattices, Boolean algebras for encoding records, extensible records that we're actually trying to hopefully smush together with our theory of subtyping with their theory of Boolean algebras. So come back in a couple of months and hopefully we have an answer for you. But we're trying to write that up right now. So we're trying to work out the details. Hopefully it'll be figured out in 2 weeks, but fingers crossed.
Hi, cool talk. So this reminds me a lot of universal polymorphism in dependent type theory, and especially like with subtyping cumulativity. Can you speak to more about the similarities and what ideas were sort of borrowed from that, and what can be maybe brought back? That sort of
capture tracking came out of a capture tracking capture track, I guess, is inherently, which this work was kind of inspired by, came out of a fairly dependently typed system because it has term variables in type position, these qualifier sets and these capture sets, right? We've tried to avoid like dealing with dependent types as a concern that's orthogonal to us. We did give an encoding of capture tracking in the paper that gives a lightweight form of dependent type theory, but really lightweight in the sense that you have to annotate, you have to effectively annotate at your call sites what should be substituted in capture position to avoid a lot of the pitfalls that we had designing capture tracking with monadic or form or variance that really caused a few landmines. So yes, maybe, hopefully, is the answer. Hopefully that answers your question.
You had a lot of nice meta-mathematical properties,
right,
which is great. But one thing I didn't get a good intuition for is, did it actually work on, did you try it on a bunch of programs? I mean, it looks very promising, but I just wonder if there's some incompletenesses. I mean, that's really more.
Well, I guess like the universal algebra gives you the fact that like this does encode the right thing because like everything you want, anything that you want abstractly you should be able to prove in the free lattice setting. Have we tried this on programs? No, this is strictly a theoretical paper. We are working on an implementation on an extension with the Flix people, but like I said, I'll hopefully get back to you soon about that.
Okay, thank you, Edward. Great talk.
Hi. All right.
Actually, still have about a minute or so. Might have to wait a little bit for.
Okay, that's no problem. Let me plug this in. Okay, well, the minutes comes in quite nicely, I guess. Displays. Great.
Next up, we have Robin Webers talking about refinement type reputations.
Hi all, I'm Robin, and indeed this talk is on refinement type reputations, where we try to answer, the age-old question, why does my program not type check? So, what are refinement types? Well, they allow us to take a base type, add a predicate to it. For example, we can define the non-zero type by saying, well, these are all the integers whose value is not equal to 0. And we can use this type in function contracts. For example, the division function, if we divide by 0, our program will crash, and we really don't like this. So we can say, well, the denominator, it should not be 0. And then subsequently, on any cause of 0 of this division, the refinement type checker will automatically check via SMT solver that we're adhering to this property. And then similarly, if we call the division with 0, it will reject this program. Well, and what's kind of cool about refinement types is they work with all of these functional programming concepts automatically, or well, they work with polymorphism, higher order functions, type classes. So in this example where we define the natural numbers as all integers that are larger or equal to 0, if we then define some normal polymorphic functions like the max that takes the largest of two numbers, or this fold, which actually takes a higher order function, a list, and squashes this list into a single entry. We can then use this to prove some property about a program. So in this very silly example, we do a fold of max, which takes the largest element of a list, in this case of the elements 4, 3, 2, and 1. And we say, well, the output of this function, it's a natural number. And the refinement type checker, it deals with all of these cool FP ideas, and it verifies the program. But under the hood, there are some type inference going on. So we have these polymorphic type variables, A, and the refinement type checker needs to find the predicate for it. So, at first, it just says, OK, there's some predicate. We don't know what it is. It's any predicate. And it will try to find a solution for it. And a proper solution for the previous example is just saying, well, we're working over natural numbers. And the really nice thing about this in particular is we're not telling, at any point, we're not annotating any of these natural number points, right? So we don't have to specify at every application what is the type of our new function. This is all done for us. And I think that this is sort of what makes refinement types really nice to use. There's a bunch of programming languages that support them, some really cool projects in it, even some work on it for hardware. But one thing that's sort of odd to me is, well, it's very great when our refinement, when our verification works. This is only like a small percentage of the time we're actually dealing with. Most of the time, we're staring at our code and our error messages, and we're thinking, why does this not verify, right? So let's look at a small example, or the previous example where we make a small change. Namely, we take all the even type, all values, all integers whose value modulus 2 is equal to 0. And the previous example, and we just say, OK, let's not make it return a natural number. Let's make it return an even number. And suddenly this fails. And this is kind of vexing, because we can run this code, and this code returns 4. So why does our verifier not validate this program? Well, luckily, we have the error message of the validator, right? Like I work with this a lot, and even I think this is, like, I cannot really understand this part. Let's be real. And it's not just like, oh, the tool it has a bad interface. We have a good explanation for it, but we just don't tell you about it. Like it's really fundamental to this refinement type checking, because this block, this is what the type checker actually inferred for this unknown refinement at some point. So this block is machine generated, so it's kind of just unreadable for that reason. And we need to do better, because I don't want to look at these error messages anymore. So that's a problem, and we propose this solution of type reputations, which can explain typing failures even in the presence of these unknown refinements that give these very yucky representations. So I think a helpful abstraction for thinking about refinements is thinking about them as sets. So the natural number type is just the set 0, 1, 2, 3, et cetera, et cetera. If we don't know what the type is yet, an unknown predicate, you can just think of it as some set. It might be empty. It may contain many elements. We don't know what's in that. If we do type checking using these refinements, what we're really doing is just seeing, OK, for example, we have this set 0, 2, 4, and 6. If we want to check that this type is even, or the set is even, well, we just look at all the elements and see whether they're even. The opposite, though, if we're doing explaining type failure, we don't care about all entries, really. We just care about, well, one specific counterexample, right? So here we picked 1 as a counterexample. We could have picked 3, 5, whatever. But it only needs to be one counterexample. The problem is, what if we have an unknown refinement? Which element will we take? And our solution is the must instantiation. So I think it's good if we now look at sort of the constraints that were in our example program. And remember, the default, it was instantiated with this sort of unknown refinement, right? And really, two constraints arise. First, well, the elements 4, 3, 2, and 1, they all need to be inside of this constraint. And then, well, this unknown refinement, it needs to subtype even. Well, we don't really care about all these values, 4, 3, 2, and 1, right? We only care about one value that allows us to refute this. So we could have also picked 1, but in this example, we say, OK, 3 must be in this set, right? Don't care about the rest. 3 must be in this set. And 3 is enough to show that this set is not even. So this is a must instantiation. I think it's now cool if we look at a small case study to kind of illustrate how this works in practice on a less fabricated example. And then we can also look at the output of our tool. So we have this small arithmetic expression language where we have numerics. We have addition of 2 numbers. We can define a variable with a let expression inside of the body. And we have variables. And variables are defined with a natural number. So this is akin to the Brine indices. And the idea is basically, well, given that we have an empty environment, for example, and we define this variable x with a let, the variable 0 refers to its closest binding let. And this is kind of similar to evaluating this let binding, pushing it into the environment, and then the variable, it still just indexes this environment. Well, so let's define some variable lookup, right? We have a variable, which is our natural number, an environment, and we want to get a number out of this. But we can kind of go out of bounds with our variable lookup. And really, there's no reasonable behavior at this point if we go out of bounds. So what we instead will do is put on a small refinement which says, well, our variable needs to be in bounds of the environment. Well, with this lookup, we can define our actual evaluator. So the evaluator takes an expression, returns a numeric type, and we start off defining this, well, go function. This is the meat of the evaluator, and we call it with an empty environment. So what does the go do? Well, for numerics, it returns the number. For variables, we do a variable lookup. For addition, we evaluate both ends, add them up, and for let bindings, we extend the environment and then we evaluate the inner body, right? So it does all the sort of usual stuff you'd expect. Well, let's look at the counterexample that is actually generated from our tool. So here's our tool output, and at this very top, I hope, okay, that's not visible. At the very top, you see the final refutation, which says, okay, the environment, it's empty, but then it does not satisfy that X can index it, and we can actually see if we scroll down, well, the value of X was 0, and 0 cannot index it. If we're now curious, but where did this empty environment even come from? We can go to the environment, and we can expand it. And this is a must instantiation. So if we kind of click on it and traverse down the path, we can actually see, well, this is a point in time where we got an empty environment as an argument. So this sort of is an interactive way to navigate a counterexample generated by our tool. Well, so we had the case study. Now a quick eval. Well, how often do we find refinements? At the end of the day, we're doing a search to find a refutation. So in some cases, we cannot find it, but in general, most files we do find one. So what programs do we run? Well, the top 3 are from a student assignment class where students needed to verify some programs, and these are all their failing tests. The bottom one is the regression test as by Liquid Haskell, the tool we extended for the refinement type refutations. And here we can kind of check all whether it supports all the refinements that Liquid Haskell has. Well, apart from how many it can find, there's also this thing of we're doing a search essentially. So searches can sometimes be slow, but in the most case for the list, map, reduce, and regression tests, within a second or 2, we find a refutation. There's a few outliers, but that's sort of the general idea. For the k-means one, well, they were a bit slower, so you have kind of 3 data points. Either we're very fast comparative to MapReduce or the other tests, or it takes 1 minute, or it takes 120 seconds, around that time. We kind of attribute this to this example just having a very large state space. So, finding a counterexample sort of degrades once the example gets really big, or at least, when there's a lot of unknown refinements in sequence. So, in summary, the previous error messages were absolutely unreadable. In our paper, we define must instantiations as a theory to refute refinement types even with these unknown refinements. And we built a tool which allows us to both find a counterexample and then interactively explore this. That's my talk. Thank you.
Hi, thanks for the talk. So there was a tool from EPFL called Leon. Now I think it's called Stainless. It uses SMT solvers to do verification of contracts. So it's not exactly refinement types, but they had this very nice property that it was a counterexample complete. So if it failed to verify, it will actually give you a value that makes the contracts wrong, right?
Okay, yeah.
And this is possible because to verify this in SMT solvers, you just take the universal formula you want to contradict, you negate it, and then the SMT solver just gives you the actual instances.
Yeah.
Yeah. So why can't you do that
So
in liquid Haskell?
The constraints for liquid Haskell are constraint horn clauses, which in general mean, like, so this example, well, we have, let me click back. Oh boy, that's a lot. Okay, anyway, I feel like I'm never going to reach it. The unknown refinements, there can be many constraints that say, okay, you know, the unknown refinement has to have this constraint, but it can be constrained by n amounts of calls, essentially. And then, well, how do I put this? Okay. Maybe if I, yeah, I mean, so these are two constraints, right? So it's kind of two implications you can think of. One implication is, well, 4321 needs to be in this set. The other one is, you know, this set needs to imply even. We can have, like, a lot of these. And also, we can have a lot of these, all talking about the same, you know, unknown refinement. And even,
but if you put a problem like this in an SMT solver, it should give you a counterexample. It should give you an instance that makes the problem.
I mean, so essentially, this is what we're doing, right? But there's not one unfolding. We need to, like, it's kind of a tree of paths.
Okay.
Because there's multiple, you know, constraints on these unknown refinements.
All right.
And that's what makes it a search as well. So, like, any one of these constraints may be the cause of non-type checking. Yeah.
Okay. Thanks. Yep.
Thanks for the talk. So I know that your presentation was kind of high level. So this will probably be just a quick yes or no yes or no answer. But like one of the things that I've observed in sort of writing my own refinement types is that a lot of the times when I get this type of error, usually you have this sort of, the must inference that the counterexample comes from an illegal state. Like I have underspecified my program. So does your technique or permit or allow for the extension to do sort of like must not inference so that you can automatically sort of pinpoint the part of the code where the problem is and then say, if you specified this with a stronger specification, we could have the program type check.
Right. So I guess like the first example, or actually this example is an example where, you know, the constraints don't really do what you'd expect. The program is under constraint, right? We don't really have a way to pinpoint exactly where this under constraining happens, but you know the tool does help you with finding where values don't match up the way you'd expect them to, right? So we would not really expect 4321, like the whole list, to influence this type, right? We ideally want full R1 max to tell us something about this type. So in this way, we can kind of find out where the under constraintness comes from. But no, we don't have a way to say, OK, it's exactly this point.
Got it. Thank you.
Hi, thank you for the talk. So do you think that this technique would help all the error messages that you can have in Liquid Haskell, or just a small subset? And if just a small subset, are there other improvements that you think should be made?
So this actually works with pretty much all the sort of refinements we have in Liquid Haskell. Also, so I don't know if you're familiar with like abstract or bounded refinements, for example. It works for those, although you know, perhaps the error messages get a little bit more vague for them. But yeah, at least there's some error message for it. I haven't looked at it too much, I will say. So maybe for those, like there's a better thing we can do. Okay. But I think for almost all refutations or all failing type attempts, it kind of boils down to more basic ones. So for those, it works quite nicely.
Thank you.
Thank you, Robin. Yeah. Sorry, could you remove it?
next up, we have Denis Cagnier talking about type inference logic.
Test 1, 2, does this work? No? Hello? Maybe I'll just hold it. Test. Yeah, I'll just use this. Thank you. Okay. Hello. Thank you. My name is Denis Cagnier. This is Type Inference Logics. This is joint work with François Potier from INRIA Paris and Steven Keuchel from the Vrije Universiteit Brussels in Belgium. So suppose you have a type system, and it looks like this. I thought my first slide should be inference rules. This is, after all, the type session. And you want to type check programs such as this one. And maybe you want to elaborate them, meaning you want to decorate them with explicit type annotations. How do you do this? Well, there's many approaches. If you want to do it in a principled way, then you should read this chapter in Advanced Topics in Programming Languages. If you don't have the time to read it, I'll just tell you what it says in a gross oversimplification. Basically, you take your input program, you generate a set of constraints, which you then solve, and then you use the sort of solved form to elaborate to an equivalent program with explicit annotations. I'll walk you through a worked example now. This is the definition of Boolean negation. So Boolean negation is a function. It takes an x, and if x is true, then it returns false, and if it's false, then it returns true. So you existentially quantify over any of the unknown types, and then you simply traverse the program, meaning you equate alpha to a function type from beta to gamma. Then you look at the body of the function, you equate beta to booleans, and then for each of the branches in the if expression, you equate those to the unknown existentially quantified gamma. Then you solve them. I'm going to skip over this, but there's many techniques to solve them. And you arrive at a kind of canonical solved form. You apply this to the original program, and you arrive at the equivalent program now with explicit binders. Some people call this zonking. I simply call it applying the substitution. So constraints are great because they give you a clear interface that sort of tells you between the two phases, between constraint generation and solving, what should happen. There's an intuitive semantics there. You get separation of concerns. You can now simply traverse the program and turn a big source language into a small constraint language. But what about type inference in the real world? Does it use this style of constraint-based type inference? Well, it turns out Glasskull uses this, and they've spent a lot of PhD students trying to figure out the best way to do type inference. So I'll just walk you through what the GHC does. It takes a source expression here, an expected type, and then it has this type checking monad to return an elaborated expression. And this is really what we've been doing now. So this is the if case we're looking at. We're equating sort of the predicate to be a Boolean, just like before, and then we say that the two branches should equate to bools. So this paper's question is, how do we reason about these kinds of type inference algorithms, where we have constraints and we need to reason about scoping, particularly about existentially quantified type variables. There's effectful programming happening. There's state and option. There's abstractions. We're using monads. We need to elaborate to explicitly type programs. And we have these multiple phases going on. I'll try to give you a friendly overview. And if there's some time, I'll show you the nitty-gritty details. So we're going to combine a couple ideas. Maybe some of you have read this paper. This is by François Potier in 2014. It's a functional Perl, where he comes up with this kind of idea which he calls constraints with semantic values, which is to say it's a kind of type that at the same time is a constraint that should hold, and also it would yield a program of, it would yield a value of type A if the constraints hold. And also, importantly, the value of type A can depend on the solution of the constraints. So practically for us, this allows expressing both that the type constraints from the source, that the typing constraints from the source, I'll redo that. So for us, this would mean that we can do one traversal where we both generate the constraints of the program and at the same time can already specify what the elaborated program will look like. So let's use that to define a monad interface for constraint generation. So we define some operations like pure, which allows, essentially it's a truthful constraint, so a trivial constraint that holds and just injects a value into the monad. We use bind as a way to model conjunction. We have failure in case a program is ill-typed. And then we have type equality and pick. And the type signature for pick looks kind of funny. It kind of just magically comes up with an object language type. More on this later. Can we define a constraint generator with this interface? Let's try, yeah. So here's a function called synth, which takes a typing environment and an input program and matches on it. Importantly, the output type is sort of this monadic values. This will be a constraint, and the value that we should return is a product of a type and an elaborated expression. Let's just look at the lambda case here. So we magically come up with a type. Let's call it tau1. And then we extend the typing environment with binding for x to tau1 and type the body of the lambda. And then return in the pure function type from tau1 to tau2 and an elaborated program that now has x explicitly bound to or explicitly typed as tau1. The question is, can we implement M? So is there a sort of instance for this monad interface that we picked earlier? Well, there's a kind of standard construction called the free monad instance, where essentially you don't define any semantics for the monad operations, but you simply come with a data type that has constructors for each of the operations in the monad. So each of the constructors carries the input. In this case, for example, pure carries the input A. And then there's a continuation, which we omit if it's just trivial. The equality takes, for example, 2 taus, so 2 object language types, and the continuation is just more constraints. And the pick operator uses this kind of function space from the meta language to sort of come up with a continuation that takes a tie. This is also kind of magical. I will get back to this. So now we've defined synth, and the question is, can we prove that synth sort of overlaps with our declarative type system? So the second idea that we'll use is something called domain-specific reasoning. There's this nice quote from a beautiful paper by Nigon and Dagon, where they say that every monad deserves its own Hoare logic, essentially. And we're going to use this to kind of define a denotation of constraints. So essentially, we define this funny-looking function called WP, which is essentially program logic for constraints. So given a constraint of type free A, and a postcondition that takes an A to a proposition, we can define what that means, essentially. The important case here is the pick case, where we essentially use the meta-language propositions to existentially quantify type, and then, we existentially quantify it in such a way that the constraint will hold. So this is kind of like an angelic choice, if you're familiar with program logics. If you're having trouble sort of getting an intuition for this stuff, you can ask a program logic expert, and they will say something like, if you have the WP of some constraint and a postcondition, then what this really means is that there exists a value such that the constraints that the constraint can produce for which the postcondition holds. So equally, you can say that the constraint can satisfy the postcondition. Using this, we can now define an algorithmic typing relation. Algorithmic with scary quotes, because it's still essentially a non-deterministic program. And then we can define what that means. Essentially, we can say that there's, so the algorithmic typing relation is now defined as being able to produce the pair of tau and E prime. We now have the correctness from before, which we can now state as a bi-equivalence or a bi-implication from the algorithmic to the declarative typing. This boils down into 2 directions, which are commonly called soundness and completeness. Maybe we'll look at completeness first. So this says, given a typing derivation, we should be able to get an output of the inference algorithm. And then the goal here is just in a standard program logic style, or the standard deductive verification style, construct such a WP statement using the program logic rules from before. Soundness is a little bit more tricky. Essentially, we have to destruct this WP statement because the algorithmic typing is now an assumption. So maybe we can try something else. We can define a dual semantic. So recall we had WP before. We can now define WLP, where we essentially allow failure. So this is liberal in the sense that failure in the constraint is allowed. And we flipped what were previously conjunctions in the E case to implications, and an existential quantifier into a universal quantifier. And what this allows us to do is essentially rewrite statements of the form WPCP, so maybe we should put parentheses here, implies Q into WLP statements. And so recall that WP meant that some execution of C satisfies P. And now WLP will say that all executions of C satisfy the post condition. And then there's this theorem which you can prove by induction on C that these two overlap. This is not true in general, but it is for our semantics. And now soundness can be rewritten not as destructing the WP, but instead constructing a WLP according to this dual semantics. So you can use program logical rules here as well. That was the friendly overview of doing soundness and completeness for this kind of stuff. I'll give you, in a lightning round, what the rest of the paper was about. So you've now learned the first 2 pages of our paper. So it turns out using this function space of the meta language for modeling the pick operator is kind of cheating, because you're using a higher order abstract syntax to sort of hide the freshness and hide the scoping of existential variables. So instead, we do what a lot of people do nowadays, which is use Kripke indexing. So we have worlds where we explicitly track the variables that are in scope, and then we restrict types which are now indexed by a world to only be allowed to index those type variables that are in scope. And now we redefine the sort of the free data types, so the constraints, using this explicit notation for bound variables. So they're now essentially a family of types, so a family in the sense that for every world you can define such a type. And then with some handy notations to hide a lot of the world indexing, we redefine a bunch of the stuff that we did earlier. So here's now a new monad interface. You might see that box in the Oh, it works again. Okay. Yeah, thanks. So we redefined the monad interface, and now we are working with this kind of explicit substitutions everywhere. We redefined the constraint generator again. This thing keeps cutting out. It's kind of annoying. Yeah, thank you. So we also have constraint solving here, and then we have this run function, which essentially takes a program, sort of a constraint, turns it into pre-next form, then tries to solve it. I'm going to skip over some of this. Essentially, instead of using propositions in the meta logic, we now index them by assignments, which is to say a kind of ground link substitution to all unification variables to monotypes. And we use this as additional knowledge in the proofs. Essentially, we can sort of pretend that we already have a solution and track that there. We lift all the logical connectives to this new assignment index, and then we can restate correctness in terms of this logic. We mechanize all this in Coq, just for fun, I guess. We split it into 2 categories. So there's this generic category and the specific one. We looked at lambda bool. We're hopefully going to generalize this to a number of type systems. But the spec to proof ratio is pretty good. I don't know if you've done mechanized proofs in Coq before, but typically you don't get close to 1-to-1 ratio, so that's pretty neat. And then we also did code extraction to Haskell for our tiny type inference algorithm with a toy parser and pretty printer. And then there's a bunch of stuff that I didn't talk about. So there's another proof method with using logical relations, or Kripke indexed logical relation. We used Iris for proof automation. There's constraint solving, and then various interesting type systems that we still should extend to. That was my talk. Thank you.
Thank you, Denise. Are there any questions? Then please step up to the microphone there.
Whoa. Yeah, really great talk. Thanks so much.
Thank you.
I think I was following along with the math for a while, and then suddenly modalities appeared kind of out of nowhere. Could you please motivate that and, yeah, kind of explain where that came from?
Yeah. So essentially, I wanted to make 2 talks, and I chose to give one, which was the high-level overview talk. But there's another talk that I can give to you, maybe offline, if you're interested. Essentially, sort of what I shoved under the rug for the first 10 minutes is this this scoping of existential variables. So essentially, here in this definition, for the constructor of pick, I'm using higher order abstract syntax to hide away sort of the binding of an existential variable. And so the rest of the paper, which is the part that I swept under the rug, is making this actually explicit and tracking this, because it's quite important to the proof correctness. You want the scoping to be correct. And then essentially, once you're working with this sort of monotonic state, a very nice way to reason about it is using these Kripke, is to use Kripke indexing and have a bunch of these modalities. I don't have the slides that show the modalities here, but maybe offline I can show them to you, and we can talk about it. Thank you.
Yeah, great. Thanks.
Hi.
Thank you so much for the talk. So on the earlier slide, when you first introduced the type checking monad, I was wondering what the pick does. I don't think I'm fully on top of that, because other things I kind of understand that it's just a normal monad, but what does the pick do, and why is it there, and why does it have to be there?
Yeah, that's a really good question. So essentially, we're defining an interface here, and it's not clear whether there's actually an implementation of this interface. And because it's not clear, we can essentially do whatever we want. We can have an operation that sort of magically comes up with a type, which is what this operation does. And we're sort of thinking about ways to implement this interface later on. So the intuition for the pick operator here is basically what I just said. So you can just think of it as magically come up with a type.
Okay. So would all of the instances of like these kind of monads have this pick, and like, so why is it implemented? I'm more like confused of like what's the incentive of having this operator in this interface?
I can show you the constraint generator again. Maybe I'll show you slide 1. Maybe you look at the bottom left type inference, the bottom left rule here. So this is a typing rule for lambda abstraction, and it says that you can conclude basically in the bottom lambda x dot e admits this function type from tau1 to tau2, provided that you can type the body of the lambda e in a context that's extended with a binding for x to tau1. And what this is really saying is we need to somehow come up with tau1. And then this operator in the monad is in particular allows you, if I can find it, to magically come up with this. So if you then look at the implementation for synth, sort of the first line of the lambda abstraction is saying magically come up with a type.
Okay. Yeah, that makes sense. Thank
Cool.
you.
Cool. I do have a quick question, maybe.
Sure.
Which is, you said that the COG code and the specification were actually pretty close in number, which is pretty impressive. Do you have any sort of intuition for why that is?
Yeah, so we're very careful to sort of keep automation very high. That is to say, we hide a lot of what you would normally do, which is explicit reasoning about substitutions. We hide this under the modality stuff that I will talk to the gentleman from the first question about. And then essentially what we did is we instantiated this Coq library called Iris, which is essentially a library that implements a separation logic, also called Iris. But importantly, what they do is they have this this proof mode that allows you to sort of reason with modalities, introduce them and eliminate them very easily with a lot of proof automation, which is also what we did. But this is not a separation logic. Thank you.
code it.
Okay, so for the final talk of the session, we'll have Songlin Jia talking
Wait, where is it?
about polymorphic reachability types.
Yeah, I'm having a hard time limiting him through the two strings, but okay, here we go. Yeah, hi everyone. I'm Songlin from Purdue University, and today I'm going to talk to you about our work on polymorphic reachability types. This is a joint work together with Guannan, Oliver, Yuyan, and Tiark. This work has been accepted to POPL earlier this year, and it's our great pleasure to present it here again in person. Looking at the trend of typed system programming languages, Rust perhaps gets most of the attention. It offers many much desired features, including memory safety, thread safety, and pretty good performance comparable to C. The secret sauce behind Rust is the ownership type system, which tracks how resources, especially memory resources, are used. As a culmination of decades of research on ownership types, Rust has become the most admired programming language voted by programmers, even though it is known to be a challenging one. Still, Rust is far from the last language on Earth. Aiming to be a low-level language like C, Rust focuses especially on memory resources. In high-level languages, even though they usually come with automated memory management, tracking the ownership of other resources and their associated capabilities can enable a whole new class of programming paradigms. Following this thread, high-level languages are already motivated to build their own ownership tracking mechanisms. To name a few, Mojo from Modular AI, Swift from Apple, and some OTAML variants from Jane Street. They're all adding some Rust-style ownership types into existing high-level languages. Academic works also reflect this trend. Various substructural type systems have been studied over decades, and recently there's a Haskell extension on linear types, and SPLASH 3 also introduced capturing types, aiming to ensure safe use of effects. Despite all these proposals on combining functional abstractions and resource tracking mechanisms, there's an inherent tension between Rust secret sauce and the pervasive sharing style of programming. By Rust secret sauce, we mean its shared editor mutable principle. A resource in Rust can either be shared or be mutable, not both. On the other hand, in higher order functional programming, we use first-class functions everywhere. These functions can capture free variables from their defining environment, and they can even escape from their defining environment. Such capturing gives us a flexible form of implicit sharing, and it gives us the expressive power of functional languages. However, they do make tracking ownership and mutability hard. A concrete example of this tension can be seen in this pair of counters. A reference C can be shared in two closures through which the users can make different mutations. While this is a very common pattern across functional programming and object-oriented programming communities, it clearly violates the Rust principle. Rust is actually right here, since a race condition can occur if the two closures are used in different threads. However, it is too conservative, as serial invocations to these two closures are actually safe. So an ideal type system should be able to return the right of decision to the user so that they can avoid the unsafe cases and continue to use the safe cases. The recently proposed reachability type is such an instance. It allows tracking shared resources at a type level. For example, the CTR counter object marked on the superscript here. Usage code can later use this sharing information to ensure safe and flexible behavior. To quickly wrap up, Rust starts with a strict global invariant and selectively relaxes the usages through borrowing. In contrast, reachability types start with a more liberal sharing foundation and users can selectively restrict program behaviors on function abstractions. In this work, we build on the top of reachability types and further address the issue of combining them with polymorphism. Specifically, we propose a new notion of freshness, and our new design offers both lightweight and quantified reachability polymorphism. So let's start with some gentle examples. The first key idea is to augment the type system with a qualifier, like Edward has just introduced. So qualifier here in our system is a set of variables that can be reached from the evaluation result of the term E. For example, we can define a variable x bound to a newly allocated reference cell, and the typing of this variable tracks its own variable name, so just x on the qualifier. When we further assign x to y, the type of y will also be qualified with its own variable name. We can later transitively trace its reachability using the typing context. And for primitive resources, such as integers, their qualifier is just an empty set, meaning that they are untracked. Function types also have a qualifier, which is basically the free variables captured by the function, or the function's observable context, we call it. Now the question is, what should the qualifier be for a newly allocated value which does not yet have a name? One possible option is to assign the bottom qualifier since the new reference shares nothing with the environment. However, in this way, we're basically confusing fresh values with untracked values. Either we take fresh values as untracked, which is not summed, or we take untracked values as fresh, which is not precise, and the system becomes non-parametric, like our prior work does. Another option is to assign the top qualifier indicating this value is part of the sharing universe. This is a solution adopted by Scala capturing types, I understand, but the drawback here is that such a top qualifier is also used with all existing values, and thus, additional mechanisms are required to establish the concept of separation. For those curious minds, their degree of separation work is scheduled to give a talk tomorrow. So the new idea of this work is that instead of using either the top or the bottom qualifier, we can designate a special marker for freshness indicating something statically unobservable. In our design, we use this diamond notation for the freshness marker. These unobservable variables or locations may materialize to actual locations during evaluation. So for example, this new ref expression becomes a fresh location after one reduction step. And thus, the freshness marker in its type will be substituted with the new location. A fresh expression can also be bound as a named variable. And importantly, bound variable qualifiers are not subtype of freshness, since they are no longer unobservable, and otherwise we will lose tracking on them. So in this way, we no longer have the conflation of untracked and fresh resources, and it further gives us a parametric treatment of reachability. An important use of this freshness marker is to support both scoped and non-scoped introduction forms of resources. For example, here we have a try combinator which executes a function. This try combinator provides the capability to throw an exception to this function. We do not want this can throw capability to escape, or otherwise exceptions can be thrown outside this trying block, becoming unhandled. So in our type system, this is secured since the qualifier of the can throw capability is C, which is not a subtype of the freshness marker. On the other hand, we can also support non-scoped introduction forms. For example, we can just return a new reference cell from the function body. This works because it is fresh from the beginning. Compared with Scala capturing types, thanks to the expressing power of freshness notion, our system enjoys a more unified treatment as we don't have to differentiate scoped and non-scoped resource types. Other than sharing and aliasing, we're also interested in tracking separation among variables. Our one natural thought is to retrieve the fact of separation from the typing lattice. But from this example of intersection type, we know that such separation subtyping is hardly derivable syntactically. So what do we do? On the other hand, Our newly introduced freshness marker is already a witness for separation, meaning that the fresh notations are separated from all existing variables in the context. While this is a property too strong, here we introduce a generalized version of freshness. We call it observable separation. So by putting a freshness marker on function arguments, we are saying that such arguments are separate from all free variables captured in the function. So let's see a trivial example. This involves the identity function, which carries an empty qualifier, meaning that it captures no free variable. So then that basically means we can pass arbitrary arguments to this function, since everyone is separate from the empty set. Here's a more interesting example where we have two references, C1 and C2. The function addRef captures C1 and tries to mutate it. The formal argument R is declared with the freshness marker, and thus we need to check separation at the time of application. We cannot apply C1 to addRef as the argument, because both the function and the argument can reach C1, and thus C1 is not fresh for the function. The function can accept C2 as an argument, as the reachability intersection is empty. In the above examples, we use the empty intersection of reachability qualifiers to infer the separation of their corresponding locations. This is summed because the underlying invariant enforced by our type system. We can additionally describe the permissible overlap or permissible aliasing pattern on separated arguments by adding variable names into the argument qualifier. So for example here we add C1 into the qualifier of R for this addRef2 function, and thus applying addRef2 with C1 is perfectly okay then. Ensuring separation is very useful in many applications. For example, in the paper, we have shown how to type parallel evaluation combinator, this part that only accepts two sounds with disjoint qualifiers. In this way, we can ensure that non-interference if we run these two sounds in parallel. In this example, the part combinator takes two sounds, one captures C1 and the other captures C2, which is safe. On the top of our design, our calculus offers two forms of precise reachability polymorphism. The first form is lightweight in that it does not require an additional reachability quantifier, and the argument name itself is directly used for abstraction. So for example, in our old friend, the identity function, the resulting qualifier can depend on the input argument x. And there is no loss of precision when applying with any kinds of arguments, since the dependent x will be substituted with the actual reachability. The calculus has also been extended with bounded parametric reachability in the style of system F sub. In this way, we can introduce an additional quantification variable for reachability. For example, the z variable here. This is very useful for expressing polymorphic data structures as well as reachability tunneling, as shown in this pair example down below, where we can build a pair and its component reachability are preserved after projecting the components of this pair. So we have formalized our system with a simply typed version and also a version with F sub style bounded quantification. We have also shown the typability of church encoding of pairs in our F diamond subsystem. We have proven the syntactic soundness of our system using progress and preservation, and our preservation additionally shows that the qualifiers may only grow because of new allocations. One important corollary we have is called preservation of separation, meaning that two separate terms remain separate during evaluation. Our proofs are metronized in Claude, and there is also a prototype implementation. We call it the diamond language, which you can find in this link and in the tutorials shown here. There's also a series of ongoing work around reachability types. We have been trying to make alternative proofs in logical relations involving more properties, including termination, effect safety, and program equivalence. We're also investigating our design for subtyping and necessary reference, making our calculi more capable of non-trivial structures and more practical. You can also scan the QR codes for on these slides from some of our TED reports and paper drafts. So to conclude, we have proposed polymorphic reachability types with an explicit notion of freshness. It tracks sharing and separation in higher-order generic languages. It provides a foundation to be used in almost any impure functional languages, and it paves the way for integration of reachability types in practical polymorphic languages. Thank you all for listening, and I'm happy to take questions.
Thank you.
Thanks. This is really cool. I'm a little bit curious what it looks like in your real implementation, because like all the examples you showed were using superscripts and things I can type in my word processor, but not in source code.
So
Can
you're
you say a
asking
little bit about
the
that?
annotation burden. Okay. So
Yeah, because I assume people have to write these types, right?
yeah. So let me just do some time traveling. Okay. Here you can say that, so basically our typing of variables is very simple. We just type it to the name of the variable itself. So basically here we are doing some lazy things. So we expect you to write no explicit typing when you are, for example, within a function scope. But on function abstractions, we do expect you to state the qualifiers of the argument, since this is the intention, like what kind of argument are we expecting to accept? This is a safety guarantee that we expect developers or programmers to provide, actually. And other than that, we actually have our type system implemented in the bidirectional typing way, so we can do type inference in all other cases, I believe.
Okay, but like at module boundaries, you still have to specify the types, right?
So sorry?
At module boundaries, you would have to specify the types.
Yes, yes.
Yeah, okay. So I wonder, I guess as a follow-up, I mean, your types have sets of variables in them, right?
Sets of variables in them, yes.
So I'm worried, should I be worried that these sets can blow up and that we would get really large and unwieldy types?
Very great question. So first of all, I want to ensure you that sets never blow up, because they are all variable names. And we know variable names in a certain programming is always finite, right? So this part can be ensured. Yeah, of course, right.
If I have n types and n variables, that could be n squared.
Yeah, good question. But
maybe there's no problem. I'm just curious, right?
Yeah. So basically, we believe that the total sets of all variable names in your scope is the upper bound of the qualifier you can get. This is one part of it. And the other part of it is actually, there are some subtleties in our subtyping design, but we have been proving that our algorithmic version of subtyping is totally sound. And we also have a slightly variant version. We also prove that it is complete. So basically, they are very usable.
Thank you.
Thank you.
Nice. So the number of variables could also be the empty set if you use point-free notation. Can you say something about how would that scale? Does the system work if you use with combinators? It's quite nice to use the variables in the language, but the points, so to speak. But if you have point-free notation, you would like it to be tracking the resources as well, I guess.
What do you mean by point-free notation?
Using combinator style programming, like in Haskell, for instance. Function compositions and so on. So you use.
Yeah, I guess I can try. Let me try to understand if that's the correct question. So currently, our language do support escaping closures. So our way of doing that is, for example, if you have a fresh variable without name and it occurs within a closure, and then we replace its name, we actually use the name of the closure to refer to this free variable, the fresh value, so that there is always something tracked. Yes, I hope this is.
Okay, nice.
Thank you.
Thanks again. This concludes our session. Let's give a round of applause to the speakers. A reminder that the student research competition is going on now in Pacific. And otherwise, have a great day and see most of you tomorrow.